Imagine, like, just for a moment, that you are the architect of a multiverse.
Oh, a literal universe builder. I like it.
Right. And in a standard mathematical multiverse, well, parallel universes exist side by side. You have a universe of numbers here, another universe of functions over there.
Maybe a universe of geometric shapes right next to that one.
Exactly. And they are neatly organized, perfectly parallel, but they never, ever interact. They are completely siloed.
Right, you can look at all of them, but they don't mix.
Yeah, a number from universe A can't suddenly reach across the void and, shake hands with a function in universe B. But today, we are looking at a blueprint for a fundamentally different kind of reality.
We're exploring a cumulative multiverse.
Exactly. This is a reality where every newly created universe physically contains and actively interacts with all the universes that came before it. It's a mathematical structure that builds upon itself endlessly.
Growing more complex, more entangled, and honestly more chaotic with every single layer.
It is wild. So that sets up our basic premise. Have we missed any nuances in the intro?
I think we've thoroughly unpacked it. Let's proceed to the actual source material.
Awesome. It is a profound shift in how we construct mathematical spaces. And it leads to some incredibly deep questions about the nature of truth and equality.
Absolutely. Today, we are unpacking a really fascinating paper by PEDRO TEIXEIRA YAGO. It's titled Hierarchies of Direct Powers, Ultrapowers, and Cumulative Powers.
And the driving force behind this paper is a fundamental tension in a field called model theory, right?
Right. Model theory is, at its heart, the study of mathematical structures using the absolute strictest tools of formal logic.
Like the absolute bedrock rules of math.
Exactly. We constantly want to extend structures. We want to take something small and familiar, like the basic counting numbers, and blow it up into a massive, infinite universe of functions.
But we are, terrified of breaking the underlying logic when we do that.
Precisely. Because if you change the rules of the universe, you risk destroying the fundamental truths that actually hold it together.
Right. If you are joining us today, you are exactly the kind of listener we love. You are the learner. You want to bypass the noise and get straight to the bedrock of a subject.
We're going to figure out how mathematicians build these towering, infinite structures.
And what happens when the logic of these multiverses starts to crack under the weight of its own complexity? Plus, how fixing those cracks inevitably leads to the discovery of one of the most mind-bending concepts in all of human thought.
The surreal numbers.
The surreal numbers. Okay, let's unpack this. We need to start with the baseline. Before we build the crazy interacting multiverse, we need to understand the standard boring one.
The baseline is crucial.
So that covers the mission statement of our deep dive. Did we miss anything there?
No, I think we've thoroughly unpacked it. Let's proceed to defining direct powers.
Great. So what exactly is a direct power? Let's really dig into the foundation here.
To understand a direct power, we first have to talk about what it actually means to build a function space.
Okay, let's slow down. What is a function space?
Let's start with a base universe. We will call it our generating structure. For simplicity, let's just use the set of natural numbers.
So 0, 1, 2, 3, and so on.
Right. That is our foundational reality. Mathematically, we define this base universe as n0 equals the set of natural numbers. Now, we want to build a new, larger reality out of this.
And we do this by introducing an index set, right?
Yes, an index set. You can think of an index set as a collection of labels, or, to use your multiverse analogy, a set of parallel timelines.
Okay, so let's say my index set is just the numbers 1, 2, and 3 timelines.
Exactly. A direct power is simply the collection of all possible functions that map those 3 timelines to our base universe of natural numbers.
Okay, I think I see. So one element in this new universe might be a function that outputs the number 5 in timeline 1, the number 8 in timeline 2, and the number 0 in timeline 3.
You got it. You can just visualize it as a sequence. 5, 8, 0. Another element might be 2, 2, 2.
So this new universe, this direct power, is filled entirely with these sequences.
Right. And if your index set is infinite, you have a universe made of infinitely long sequences.
Okay, that covers the structure of a direct power. Have we missed any nuances on how it's built?
I think we've thoroughly unpacked it. Let's proceed to how we do math inside it.
Yeah, that's my next question. How do we actually do math in this new universe? If I want to add 2 of these sequences together, how does that work?
It works through what we call pointwise operations. And this is where the isolation of the multiverse really shows itself.
Pointwise, meaning point by point.
Exactly. If you want to add the sequence 5, 8, 0 to the sequence 1, 1, 1, you just add them point by point, timeline by timeline.
Okay, so in timeline 1, I add 5 and 1 to get 6. In timeline 2, I add 8 and 1 to get 9.
Right. The timelines never cross-contaminate. The math happening in timeline 1 is completely blind to the math happening in timeline 2. Parallel, independent calculations.
So a standard direct power is like a row of identical houses on a street. You can have a blueprint of a house, and you can build 50 houses from that blueprint.
And you can have 50 families living in them, cooking dinner at the exact same time.
But the families don't interact. And more importantly, the abstract blueprint of the house doesn't physically live inside the houses alongside the families.
That is the perfect way to visualize it. The generating structure and the new functional structure are strictly isolated from one another.
So the original natural numbers don't live in the new universe, only the sequences do.
Right. You can trivially embed the old universe into the new one. For example, you can say the fundamental number 2 is represented by the constant sequence 2, 2, 2.
But conceptually, the fundamental integer 2 and the sequence 2, 2, 2 exist on entirely different existential planes.
Exactly. There is no direct interaction between the base elements and the newly constructed functional elements.
All right, that covers the mechanics of direct powers. Did we miss any nuances there?
I think we've thoroughly unpacked it. Let's proceed to the paradigm shift.
Awesome. And this brings us to that shift. This is where Teixier Yago introduces his core innovation, the cumulative power.
Right. He completely changes the recipe for how we build the next level of the universe.
And he does it by introducing a single, incredibly powerful mathematical operation, right? The union.
Yes.
No.
What does it mean to take a cumulative power? Well, in the old direct power method, when we built level 1 from level 0, level 1 consisted only of the new functions.
But with a union operation.
By adding a union operation into the definition, the author is explicitly taking every single object that existed in level 0 and dumping it directly into level 1, alongside all the new functions.
So it is strictly cumulative. The actual math for this next level is n beta plus 1, n beta plus 1 equals n sub beta to the power of the index set s sub beta, union n sub beta.
Perfectly stated. That union symbol means everything from the past is dragged into the present.
It's a Russian nesting doll.
Exactly. But a mathematical Russian nesting doll where you can play with all the layers at the exact same time.
The outer dolls actually contain the inner dolls as distinct accessible objects.
Right. So at level 1, you don't just have sequences of numbers. You have sequences of numbers sitting right next to the original base level numbers.
And when you build level 2, you create functions that output level 1 objects, and you dump all of that into a bucket alongside everything from level 1 and level 0.
Yes. You build this towering hierarchy across infinite stages where elements from vastly different levels of complexity all live in the exact same shared space.
That covers the definition of the cumulative power. Have we missed any nuances in the architecture?
I think we've thoroughly unpacked it. Let's proceed to the mechanical problems this creates.
Good. Because this sounds amazing for building a truly interconnected multiverse, but my immediate thought is, well, this has to be a mechanical nightmare.
Oh, it absolutely is at first glance.
If I'm trying to do algebra in this space,
Right.
the pointwise rule completely breaks down, doesn't it?
It does, completely.
If I have a sequence, let's say 4, 5, 6, which is a level 1 object, and I want to add the basic number 3, which is a level 0 object, how do I do that?
Right, you can't ask the number 3 what its output is in timeline 2.
It's just 3. It doesn't have an output. It's a rock. It's a fundamental constant.
You've hit on the exact mechanical crisis that the second part of this paper sets out to solve. You cannot apply pointwise operations to things that aren't points.
So Teixier Yago has to invent a way for these objects from entirely different existential planes to actually interact.
And he does this through two brilliant concepts. The first is the level of an element, and the second is the hereditary function.
Okay, so that sets up our mechanical crisis. Have we missed any nuances regarding why pointwise operations fail here?
I think we've thoroughly unpacked it. Let's proceed to the solution, starting with the level function.
Perfect. Let's unpack the level function. The author uses a specific symbol for this, right?
Yes, the level function is denoted by the Greek letter rho. Because this hierarchy is cumulative, an element exists everywhere once it's created.
Right. If the number 3 is born at level 0, it gets swept up into level 1 and then level 2 and all the way to infinity.
Exactly. The level function, rho, simply looks at an element and identifies its exact birth date.
It asks, at what stage of this infinite construction was this specific object first generated?
Right. For the basic integer 3, its rho is 0. For a function that outputs natural numbers, its rho is 1. It isolates the foundational origin of the object.
I really like that. It's a birth certificate. It tells you how fundamentally complex the object is, regardless of what layer of the multiverse you currently find it in.
Precisely. So we have a way to identify the complexity of our objects.
That covers the level function row. Have we missed any nuances about birth dates?
I think we've thoroughly unpacked it. Let's proceed to how we use these levels in operations.
Right. How does knowing the birth certificate help us actually add a level 1 function to a level 0 number?
This brings us to the highest level dictates rule. When you want to perform an operation, like addition, on a group of elements from different levels, the mathematics instantly looks for the element with the highest birth date.
The highest row value.
Yes. Let's say you want to add a level 5 object, a level 2 object, and a level 0 object. The operation snaps to level 5.
The highest level sets the rules of engagement for the entire interaction.
Exactly.
It's like a corporate hierarchy. If you have a meeting with the CEO, a middle manager, and an intern, the meeting is run according to the CEO's schedule and the CEO's rules.
That's a great way to think about it. The intern just has to adapt.
But mathematically, how does the intern, the level 0 number, adapt to a level 5 operation?
This is the absolute genius of the framework. To make the intern adapt, TEIXEIRA YAGO introduces the hereditary function.
And this is another Greek letter, right?
Yes, the hereditary function is denoted by the Greek letter for theta theta.
Okay, that covers the highest level rule. Have we missed any nuances there?
I think we've thoroughly unpacked it. Let's proceed to how the hereditary function actually operates.
Let's do it. What does var theta theta actually do? You mentioned earlier it's kind of like a translator.
Yes. You can think of the var theta theta function as a mathematical universal translator, or perhaps a temporary promotion mechanism.
A universal translator. I really like that. How does it translate?
Well, the operation is happening at level 5. The var theta theta function looks at each element involved.
If it looks at the level 5 element, it says, great, you speak the language, give me your output.
Right. But when it looks at the level 0 element, our basic integer 3, it recognizes that this element doesn't have outputs. It's beneath the level of the operation.
So the var theta theta function essentially says, I will promote you.
Exactly. It treats the lower level constant as if it were a constant function spanning the entire higher level space.
It defers the rule down the hierarchy until it finds a level where the object actually knows how to behave.
Yes, it recursively translates the demand downward.
That covers the concept of the hereditary function. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to a concrete mathematical example.
Yes, let's make this incredibly concrete for the learner, because the paper actually provides a fantastic visual example for this.
It does. The author asks us to calculate a specific sum. We are adding a level 2 function to a level 0 constant.
Specifically the number 3.
Right. Let's walk through that behaviorally. A level 2 function is a function that outputs level 1 functions.
Visually, you can imagine this as an expanding tree, or as the paper writes it, a column vector where every entry is a row vector.
Yes. So our level 2 object is essentially a list of lists.
The first list might be 1, 1, 5, 8, and so on. The second list might be 1, 3, 7, 9. It's a complex nested structure.
And we are trying to add the single basic number 3 to this giant list of lists.
Under the highest level dictates rule, the operation happens at level 2.
Right. The universal translator, the var theta function, looks at the number 3 and says, you need to be a level 2 object for this to work.
So it promotes the 3. It turns it into a list of lists where every single entry everywhere is just the number 3.
Exactly. And once the translator has done its job, the addition just happens naturally pointwise.
The 3 permeates the entire structure. It reaches down into the very bottom of the Russian nesting doll and adds itself to every single base integer.
So that first list, 1, 1, 5, 8, becomes 4, 4, 8, 11. The mechanics work flawlessly.
You have successfully created a unified algebraic system where objects of wildly different complexities can seamlessly interact without breaking the universe.
It really is a masterpiece of definition.
That covers the matrix addition example. Have we missed any nuances in the calculation?
I think we've thoroughly unpacked it. Let's proceed to why this is so important logically.
Okay, because the elegance of that is staggering. If you didn't have this universal translator, if you didn't have this recursive var theta function, how would you define addition across these levels?
It would be a nightmare of infinite proportions. You'd have to write a custom piecewise rule for every single possible combination of levels.
You'd need a rule for level 5 plus level 2, a totally different rule for level 8 plus level 1.
And a third rule for level 10 plus level 10. And as the arity of your functions increases, if you have functions that take 3 or 4 inputs, the number of custom rules you'd need grows factorially.
It would be an unwritable, infinitely long textbook of rules.
The var theta function collapses all that chaos into a single recursive mechanism. It defers to the established rules of the lower levels. It is a masterpiece of economic mathematical definition.
So that covers the necessity of the hereditary function. Have we missed any nuances there?
I think we've thoroughly unpacked it. Let's proceed to the logical consequences of this structure.
Awesome. Okay, so we have successfully built our cumulative multiverse. The architecture is sound, the algebra works. A level 5 object can shake hands with a level 0 object.
There is a but.
There is a massive but. If you're listening to this and you remember how we started this deep dive, you know that model theory isn't just about making sure you can add numbers together.
It's about preserving the logic of the universe.
We have to ask the critical question. Did we break the underlying truth of the mathematics? What logical rules actually survive this massive, towering construction?
And this is where the paper takes a very dramatic turn. To understand what survives, we have to talk about how model theorists view logical sentences.
Imagine a formal logical rule, something like, for every number x, there exists another number y, such that y is greater than x.
Yes, that is a first-order logical sentence. Mathematicians have spent decades figuring out which types of sentences survive when you build these multiverse structures.
For example, back in the 1950s, Alfred Horn proved that a very specific, somewhat restrictive type of logic called Horn sentences are perfectly preserved when you build direct products.
And the paper mentions that in the 1960s, a mathematician named Weinstein figured out the exact fragment of logic that survives in direct powers.
They literally call them direct power sentences.
Right. But our cumulative multiverse is fundamentally different from a direct power. We have elements from different levels mixing together.
So what happens to our logic?
They're splinters.
That covers the historical context of logical preservation. Have we missed any nuances there?
I think we've thoroughly unpacked it. Let's proceed to why the logic splinters.
Let's get into it. Why does it splinter?
The reason it splinters comes down to the defining tension of this entire paper, the definition of equality.
This is the crux of the whole thing. Let's really dig into this. We just established that we have these beautiful hereditary relations, like our addition example, or concepts like greater than.
Right. These relations are perfectly comfortable reaching across the levels of the multiverse. The universal translator makes it work.
But equality is different, isn't it?
Radically different. In this raw cumulative hierarchy, equality is defined as strict, literal, ontological identity.
Meaning two things are mathematically equal only if they are the exact same physical object with the exact same birth date.
Exactly. The row values must match.
Let me throw an analogy at you to make sure I have this locked in. It's like having an actor playing a doctor on a television show and an actual licensed medical doctor.
Ooh, I like where this is going.
Behaviorally, within the context of the hospital set, they might say the exact same medical jargon. They might look at a chart and both say, the patient needs a bypass.
A hereditary relation, like the action of diagnosing, looks at them and says, yes, they are both performing the action perfectly. They are functionally identical.
But strict equality looks at them and says, absolutely not. One is a human holding a script who was hired yesterday, essentially level 1.
And the other is a human with a decade of medical school who has a license, essentially level 0.
Right. They are fundamentally legally distinct entities.
That is a phenomenal analogy. And the mathematical structure of the cumulative power violently enforces that distinction.
That covers the definition of strict equality. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to what this does to logical formulas.
Yes, what does this strict identity rule do to the math?
Because of this strict identity rule, the paper proves that the only logical formulas that survive the cumulative construction are what it calls non-collapsible formulas.
Non-collapsible. What does that mean behaviorally? What makes a formula collapse?
A collapsible formula is one that, in order to be true, requires two objects from different levels, different birth dates, to be strictly equal to one another.
It requires the actor to literally be the licensed doctor.
Yes.
Yes.
The structure prevents that collapse. The universe simply says, no, they are different, even if they behave identically under every other operation.
Can you give me a specific mathematical example of a logical rule that would break because of this?
The classic example the paper gives involves mixing existential and universal quantifiers, the there exists and for all statements.
Okay. Let's say you have a logical rule, exists x for all y. There exists x such that for all y where x equals some combination of y.
Right. Why does that break? Because of the order in which you pick things. The there exists part forces you to pick your object X first.
Let's say you pick a level 0 object, your intern.
Then the for all part kicks in. It says this rule has to work for every object in the universe. So it reaches up and grabs a level 1 object, a manager.
Now you have an equation that demands a level 0 object perfectly equals a level 1 object.
The strict identity rule flags a violation. The birth dates don't match. The levels mismatch.
The formula collapses and the logical truth of the universe is broken.
Exactly.
That covers the concept of collapsible formulas. Have we missed any nuances there?
I think we've thoroughly unpacked it. Let's proceed to a summary of the crisis.
So, to summarize the first half of this paper, Teiixeira Yago has built a mathematically gorgeous, interactive nesting doll multiverse where you can do algebra across infinite layers of complexity.
But the price of that interaction is devastating.
By insisting on strict literal identity for equality, the logical laws of the universe become incredibly fragile. The math is honest, but it's chaotic.
If we want this cumulative tower to actually be useful to mathematicians, if we wanted to preserve the beautiful, robust, logical truths of the base universe, we have a massive problem to solve.
We have to fundamentally redefine what it means for two things to be equal.
We do.
That covers our midpoint summary. Have we missed any nuances before moving to the solution?
I think we've thoroughly unpacked the crisis. Let's proceed to the mechanism of quotienting.
How does the author pull off redefining equality?
By taking your actor and your doctor and choosing to put on glasses that blur your vision.
Blurring the vision, I love that.
The paper introduces an incredible mechanism to reclaim the logic, and it starts with defining an equivalence relation.
The paper uses the symbol equiv beta is equivalent to at level beta, right?
Yes. Instead of demanding strict identity, Teiixeira Yago proposes that we define equality modulo hereditary identity.
Equality modulo hereditary identity. That's a mouthful. Let's translate that out of math speak.
We are changing the philosophical definition of equality. We stop asking, are these two objects the exact same fundamental entity with the exact same birth date?
Right. We stop looking at the row value.
Instead, we ask, when we run these two objects through our universal translator, the var theta function, do they yield the exact same behavioral outputs at every lower level?
If they act identically in every conceivable scenario, we declare them mathematically equivalent.
Exactly. We group them together into a single equivalence class.
That covers the definition of the equivalence relation. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to an analogy for this blurring effect.
Let me try an analogy. It's like looking at a pointillist painting.
Oh, like a Seurat painting.
Yeah. If you get really, really close to a Georgia Seurat painting, you see thousands of distinct, strictly unique dots of paint. You see a dark blue dot next to a slightly lighter blue dot.
Right, and in the raw cumulative power, strict identity forces you to treat every single dot as a completely different universe.
The actor and the doctor are strictly different dots. But if you take a few steps back, if you put on these equivalence glasses, the dots merge based on their behavior.
All the dots that act like blue merge into a single, cohesive blue expanse.
You lose the granular, nitpicky details of their origins, but you gain a recognizable picture. You are essentially blurring your vision.
Blurring your vision is the perfect way to describe a mathematical quotient.
That covers the pointillism analogy. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to what happens when we apply this quotient.
So what actually happens mathematically when we blur our vision?
When we take this equivalence relation and apply it to our massive, chaotic, cumulative multiverse, something miraculous happens.
The paper proves a major theorem here, doesn't it?
Yes, it proves that when you quotient the cumulative power by this behavioral equivalence, the entire multi-level structure perfectly collapses.
And what does it collapse into?
It becomes mathematically isomorphic, structurally identical to a standard old-fashioned direct power.
Wait, I mean, that is mind-blowing. Let me make sure I'm wrapping my head around the magnitude of that.
It is a huge structural revelation.
We started by saying cumulative powers are this wild new alternative to direct powers, but this theorem implies that cumulative powers aren't an alternative at all.
No, they are the foundational superset.
Direct powers are just cumulative powers, where you've chosen to blur your vision to ignore the structural differences between the levels.
Precisely. The direct power is just the shadow cast by the cumulative power, when you shine the light of behavioral equivalence onto it.
That covers the isomorphism to direct powers. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the logical reclamation.
So because it collapses perfectly into a direct power, what does that mean for our broken logic?
The paper confirms that this newly blurred structure preserves all the logical sentences of a direct power, not just the non-collapsible ones.
By redefining equality from strict identity to behavioral equivalence, we have reclaimed our logical consistency.
The universe makes sense again.
But the paper doesn't stop there. Direct powers are great, but in model theory, the ultimate tool for preserving logical truth isn't the direct power.
No, it is something called an ultrapower.
And to get an ultrapower, we have to blur our vision even more aggressively. We need a tool called an ultrafilter.
Yes, the ultrafilter.
That covers the transition to ultrapowers. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to defining what an ultrafilter is.
If there is one mathematical concept I want the learner to walk away from this deep dive understanding, it is the ultrafilter.
It's essential.
It sounds like a piece of coffee machinery, but it is one of the most powerful concepts in infinite mathematics. How do we explain an ultrafilter to the learner?
Let's stick with the idea of making decisions across parallel timelines.
Okay.
In a direct power, two functions, two sequences of events across the timelines, are only considered equal if their outputs match perfectly in every single timeline.
100% agreement is required.
An ultrafilter is a mathematical mechanism that relaxes that requirement. It acts as a supreme judge.
A supreme judge.
Its job is to look at all the timelines and decide which groupings of timelines are large or important enough to represent the truth of the whole system, and which are small and can be ignored.
So it's a voting system, but it's not a pure democracy. It's a voting system where some coalitions of voters are deemed so fundamentally important that they dictate the outcome, even if they aren't unanimous.
Yes, a highly structured voting system. It's almost like mathematical gerrymandering.
That covers the basic analogy of an ultrafilter. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to a concrete example of this voting system.
Give me an example of how this judge operates.
Let's say our index set, our timelines, are the natural numbers, 1, 2, 3, 4, 5, etc.
Okay, an infinite list of timelines.
An ultrafilter might look at this and declare, any set that contains all the even numbers is a large set. It holds the majority power.
And the odd numbers?
Any set that only contains odd numbers is a small set. It has absolutely no power.
Okay, so how does this judge decide equality? If I have function A and function B,
Let's set them up.
function A outputs the number 10 on all the even timelines, but it outputs 0 on the odd timelines. Function B outputs 10 on the even timelines, but outputs 99 on the odd timelines.
In a strict direct power, these are completely different functions. They disagree on half of infinity.
That covers the setup for the ultrafilter example. Have we missed any nuances?
Yes, I think we've thoroughly unpacked it. Let's proceed to the ultrafilter's ruling.
How does the judge handle this disagreement?
In an ultrapower, which is built using the ultrafilter, the judge steps in. The judge says, I see that function A and function B disagree on the odd timelines.
But the judge already decided odds don't matter.
Exactly. The judge says, I have previously decreed that the odd timelines are a small set. They don't matter. I see that function A and function B agree perfectly on the even timelines.
And the even timelines are a large set.
Therefore, by the power vested in me, function A and function B are absolutely mathematically equal.
Wow. The ultrafilter forces them into equivalence. It blurs out the disagreements happening on the small sets.
That is exactly what it does.
That covers the ultrafilter ruling. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to why mathematicians actually do this.
That is wild. It's essentially forced consensus. But why do mathematicians go through the sheer agony of inventing these judges? Why force things to be equal when they clearly aren't?
Because of a result known as Ush's theorem.
Okay, let's unpack Ush's theorem.
Ush's theorem is the holy grail of model theory. It proves that if you use an ultrafilter to build an ultrapower, the resulting universe perfectly, flawlessly preserves every single first-order logical property of the original base universe.
Not just a fragment of them, like the horn sentences.
All of them. If it was true in the base universe, it is absolutely true in the ultrapower. You achieve perfect logical fidelity.
And TEIXEIRA YAGO proves in this section of the paper that if we quotient our chaotic cumulative hierarchy using these ultrafilters at each stage,
the resulting structure is perfectly isomorphic to a hierarchy of ultrapowers. We turn chaos into pristine logical perfection.
That covers Ushi's theorem and the transition to ultrapower hierarchies. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the embedding puzzle.
Right. So we've successfully mapped our cumulative multiverse onto an ultrapower multiverse. But this leads to a massive architectural puzzle.
It's one thing to build these universes. It's another thing to understand how they nest inside each other.
The paper dives into the embedding puzzle. If I have a small universe that fits neatly inside a larger universe, does the ultrapower of the small one fit inside the ultrapower of the large one?
To solve the embedding puzzle, the paper utilizes something called the Redefining ordering.
And mathematically, this ordering uses the symbol is less than or equal to in the Redefining ordering, right?
Yes. This is a way of comparing the size or the complexity of different ultrafilters. Remember, there are many different ways a judge can define what a large set of timelines is.
That covers the introduction of the Redefining order. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to how the ordering solves the embedding problem.
So how does comparing judges help us nest universes?
The Redefining order essentially asks, can one judge's voting rules be perfectly mapped onto another judge's voting rules?
Okay.
The paper demonstrates that if your base structure A embeds into structure B, and your ultrafilter for A is less than or equal to the ultrafilter for B in the Redefining ordering.
Is less than or equal to in the Redefining ordering.
Yes, then the ultrapower of A safely and perfectly embeds into the ultrapower of B. The hierarchy holds.
That's very reassuring. That covers the basic embedding solution. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the harder embedding question.
But the paper doesn't start with the easy questions. It pushes into something much more difficult. It asks, when does an ultrapower embed into its own relative direct power?
Right. If I take the ultrapower of a structure and the direct power of that exact same structure, does the ultrapower fit inside the direct power?
To explain why this is hard, we have to talk about support and anti-support. Let's ground this for the learner. Let's use a field. The rational numbers. Fractions.
That is a perfect example of a field.
You can add, subtract, multiply, and crucially, divide any number by any other number except 0.
Correct.
That covers the definition of our example field. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to building the direct power of this field.
Now let's build the direct power of the rational numbers. We have our parallel timelines, and our functions are outputting fractions in each timeline.
You can add these functions point by point. You can multiply them point by point.
But is this direct power a field? Can you divide?
The answer is no.
Why not?
Because of the number 0. Imagine a function that outputs the number 5 in timeline 1, the number 2 in timeline 2, and the number 0 in timeline 3.
If you try to find the multiplicative inverse of this function, if you try to divide 1 by this function, you have to divide by 0 in timeline 3.
The mathematics explodes. That function has no inverse.
Because of these zero divisors, the direct power of a field is not a field. It breaks the rules of the generating structure.
That covers the failure of fields in direct powers. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to how ultrapowers fix this.
Okay, so the direct power fails to be a field because some functions hit 0. Where does the ultrapower come in?
The ultrapower fixes this using the ultrafilter judge.
Right. If a function hits 0 on a small set of timelines, the judge ignores it.
It says you're not really 0, you're just 0 in the timelines that don't matter.
Exactly. The concept of anti-support refers to these problematic zero divisors.
And the paper introduces a mechanism to ensure that when we move to the quotiented space, the ultrapower, every element is represented by a function that avoids this anti-support entirely on the large sets.
By filtering out the zeros, the ultrapower of a field remains a perfect field.
That covers the concept of anti-support. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the climax of the embedding puzzle.
This is all building to a brilliant climax. So back to the embedding question. Can I take an infinite field, like the real number line, the continuous smooth reality we use in calculus,
and take its ultrapower and embed it back into its own direct power?
Exactly. Does it fit?
The paper delivers a stark and definitive answer. No.
Never.
It proves that no infinite field has an ultrapower unless it's a boring, trivial copy of itself that can embed into its relative direct power. They are fundamentally incompatible structures.
That covers the definitive answer on embedding fields. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the philosophical why.
But why? What is physically preventing it from fitting? We just said the ultrapower is made by blurring the direct power.
Right. Usually when you blur something, you lose information. It gets smaller or simpler.
So why does blurring the universe make it impossible to fit back inside the original box?
Because the ultrafilter doesn't just blur information, it actively generates infinities.
Wait, what?
And this is perhaps the most mind-bending concept in model theory. When you apply a non-principal ultrafilter to an infinitely ordered set, like the real numbers, the voting system forces the creation of what we call dominating elements.
That covers the introduction of dominating elements. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to defining what a dominating element actually is.
Dominating elements. Explain what that means in the context of the real number line.
Imagine the sequence of standard numbers, 1, 2, 3, 4, 5, going on forever.
Right.
Now, consider a function in our multiverse that simply outputs the timeline number. In timeline 1, it outputs 1. In timeline 2, it outputs 2. In timeline 1,000,000, it outputs 1,000,000.
This function is constantly growing.
Now, we ask our ultrafilter judge to compare this growing function to the constant number 100.
The judge looks at the timelines. In timelines 1 through 100, the constant is bigger.
But from timeline 101 to infinity, the growing function is bigger.
The judge declares that the finite set of timelines, 1 to 100, is small and irrelevant, and the infinite set of timelines, 101 to infinity, is large and dictates truth.
Therefore, the judge decrees that the growing function is strictly greater than 100.
That covers the comparison to a small constant. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to scaling this to infinity.
Okay, that makes sense. It's eventually bigger than 100, so the judge says it's bigger. But if we compare it to 1,000,000...
The judge does the exact same thing. The finite set from 1 to 1,000,000 is ignored. The infinity after 1,000,000 rules. The judge decrees the function is strictly greater than 1,000,000.
And if I pick 1,000,000,000...
Same result. In fact, no matter what standard finite real number you pick, this growing function will eventually surpass it.
And the ultrafilter will decree that the function is strictly larger than that number.
Yes.
Wait, if it is strictly larger than every single finite number on the real number line, you've just invented a new number that is mathematically located at absolute infinity.
You've created a hyperreal number.
That covers the creation of hyperreals. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to why this breaks the embedding.
So how does this generating of infinity prevent embedding?
The ultrafilter forces the creation of elements that strictly dominate everything in the original universe. The ultrapower is flooded with these infinite dominating elements.
And infinitesimals too, right?
Yes, infinitesimals. Numbers that are infinitely small, but not zero. Because the direct power is just a passive container of standard sequences, it cannot mathematically hold a cohesive object that is logically proven to be strictly greater than all its constituent parts.
The ultrapower becomes too big, too alien, and too infinitely rich to ever fit back into the direct power framework.
Exactly.
That covers the resolution to the embedding puzzle. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the grand finale.
And that realization that applying ultrafilters to cumulative hierarchies generates infinity leads us to the grand finale of Teixiera Yago's paper, section 5.
The application of this entire architectural engine to real closed fields.
Everything we have discussed, the cumulative nesting dolls, the universal translator of our theta function, the blurring ultrafilters, and the birth of dominating infinities.
It all collides here to create something spectacular.
What are the final ingredients we need for this?
The paper introduces two vital components to push this to the absolute limit. First, Tails ultrafilters.
That covers the intro to the final section. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to defining a Tails ultrafilter.
Okay, what is a Tails ultrafilter?
In an ordered set of numbers, a tail is just everything that comes after a certain point. A Tails ultrafilter is a specifically chosen judge that declares that every single tail, no matter how far down the number line you go, is a large, truth-dictating set.
By prioritizing the tails, this ultrafilter is inherently and aggressively looking toward the infinite horizon of the order.
It is an engine explicitly designed to maximize the creation of those dominating infinite elements we just talked about.
An infinity engine.
Exactly.
That covers Tails ultrafilters. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the second ingredient.
What's the second ingredient?
The second ingredient is the type of space we are operating on, an ED0 set.
The paper uses the symbol Iterator not. Correct.
Yes. This is a concept developed by the mathematician Felix Hausdorff. An eta-naught set is the ultimate continuum.
It is a densely ordered space with a very specific, beautiful property.
Right. If you have a left group of numbers and a right group of numbers, and every number in the left group is smaller than every number in the right group.
You can always find a new number perfectly squeezed between them. There are no gaps, no empty space. It is infinitely dense.
Exactly. The rational numbers have a basic version of this property, but we want a fully saturated continuum.
That covers the definition of eta-naught sets. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to combining these ingredients.
Yeah, so we have an infinitely dense continuum, and we have an engine designed to generate infinity. The paper asks the ultimate question.
What happens if we take an eta-naught set, like the real numbers, and we run our cumulative power engine over it?
We nest it, we quotient it by a tails ultrafilter to generate infinities. We do it again and again and again.
And we don't stop. We run this process across all the ordinal numbers, all the way to absolute infinity.
What happens at the limit?
The mathematics in the paper, specifically theorems 5.12 and 5.13, proves that as you run this process to limit ordinals, assuming a foundational rule of set theory called global choice, the field becomes what we call saturated in every single cardinal.
That covers the infinite limit process. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to defining saturation.
Translate saturated for the learner. What is a saturated field?
It means the universe is full, completely, utterly, maximally full.
At every step of the cumulative hierarchy, you generated new dominating infinities. You push past the boundaries of the previous universe.
And simultaneously, because of the eta-naught property, you filled in every single infinitesimal microscopic gap between every existing number with entirely new sets of numbers.
Saturated means there is no logical possibility of adding a new element without breaking the foundational rules of the field. It has realized its maximum possible existence.
That is beautifully put.
That covers field saturation. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the ultimate revelation of the paper.
Here's where it gets really interesting. This is the climax of the paper, encapsulated in corollary 5.32.
It is an incredible mathematical result.
The author proves that when you run this specific cumulative hierarchy to the absolute limit across all ordinals, the resulting structure is unique.
It is the universally embedding field.
And it has a name. The paper proves that this cumulative engine constructs the surreal numbers. The symbol for this is nullers the surreal numbers.
It is a profound mathematical crystallization. For context, the surreal numbers were discovered by the legendary mathematician John Horton Conway in the 1970s, while he was analyzing combinatorial games like Go.
That covers the reveal of the surreal numbers. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to what the surreals actually are.
Conway found a way to define numbers using just two sets, a left set and a right set.
Right, and from that impossibly simple rule, he accidentally generated a number system that is so massive it has to be defined across the entire class of ordinal numbers.
Donald Knuth, the computer scientist, coined the term surreal numbers because of their dreamlike vastness.
They contain literally everything that can be considered a number.
They contain the standard integers. They contain the continuous real number line.
They contain infinitely small numbers, infinitesimals, that live in the microscopic gaps between the real numbers.
And they contain the infinitely large numbers, the omegas, stretching out forever. It is the absolute maximum extension of the concept of a number line. It is the largest possible ordered field.
That covers the scope of the surreal numbers. Have we missed any nuances? I think we've thoroughly unpacked it. Let's proceed to why this paper's proof is so important.
And what Teixireira Yago has proven here is breathtaking. Conway originally constructed the surreals through the logic of combinatorial games.
But this paper proves that the surreal numbers aren't just a quirky byproduct of game theory. They are an inevitable architectural consequence.
If you take the basic concept of a mathematical multiverse, if you say, I want my universes to interact cumulatively, and I want to preserve my logic using ultrafilters.
And you run that mechanical framework to its logical conclusion, the surreal numbers naturally, inevitably crystallize out of the void.
It proves that the cumulative power hierarchy is a fundamental architecture of reality.
Exactly. The surreal field is the ultimate destination of the cumulative journey.
When viewed through the correct mathematical lens, the chaotic nesting dolls we started with resolve into the most perfectly ordered, expansive, and ultimate number system known to human mathematics.
It is a stunning unification of model theory, topology, and algebra.
That covers the grand conclusion of the paper. Have we missed any nuances?
I think we've thoroughly unpacked it. The mathematical journey is complete.
We have been on quite a journey today. We started with a very basic visual question. How do we make parallel mathematical universes interact?
We saw the pristine but sterile isolation of standard direct powers.
We witnessed the birth of the interactive multiverse through the cumulative power, the chaotic Russian nesting dolls.
We had to navigate the sheer mechanical complexity of inventing a universal translator, the hereditary var theta function, just to allow an intern to talk to a CEO.
And then we hit the wall of strict identity. We realized that insisting on perfect ontological equality shattered the logical truths of our universe. The actor is not the doctor.
But then, by making a profound philosophical shift, by quotienting the hierarchy,
By choosing to put on the blurring glasses and judge elements by their behavioral equivalence rather than their strict identity, we reclaim the logic.
we spawned ultrapowers. We empowered judges to generate dominating infinities.
And finally, we ran the engine to the end of time, to the end of the ordinals, to witness the birth of the surreal numbers.
It's an incredible narrative arc for a mathematical paper.
This whole deep dive, this entire complex tower of mathematics, turned on a single vital pivot point, the definition of equality.
When equality was defined as strict, uncompromising identity, the math was incredibly complex, fragmented, and broken.
The universe was honest, but it was unlivable. But when mathematicians allowed for equivalence, when they judged things by how they behaved, how they interacted, and what they produced, rather than demanding they be fundamentally identical at their origin, the entire universe of surreal numbers opened up.
The ultimate continuum was born from a willingness to blur the lines of strict identity.
It makes you wonder, beyond the math, in our own pursuit of understanding the world, and in our understanding of each other, how often are we holding ourselves back by demanding strict identity?
That's a deep thought.
How often does our obsession with finding exact matches blind us to the bigger picture? Perhaps, just like in model theory, looking for behavioral equivalence, finding the places where things align in purpose and action, even if their origins are different, might be the key to unlocking an entirely new universe of possibilities.
A completely new reality.
Thank you, learner, for joining us on this incredible deep dive into the architecture of infinity. Until next time, keep exploring the structures beneath the surface.
Imagine a universe where the number 2 is just not equal to the number 2.
Right, which sounds completely absurd at first.
Totally. Not because someone made, like, a calculation error or because the laws of addition suddenly broke down, but because one of those 2's is made of slightly different mathematical DNA than the other.
Yeah, it completely shatters your intuition.
I mean, if you looked at them, they'd both act like a 2, they'd both add like a 2, but the fundamental fabric of that reality says, no, these are entirely different objects.
Because we're so used to the idea that if something behaves exactly like a duck in every conceivable scenario, it is mathematically equal to the duck.
Right.
But when you get into deep structural mathematics, you realize that equality is not a universal truth. It's a dial.
The dial. Yeah.
And depending on how strictly you tune that dial, you entirely change the geometry of what can exist.
And that is exactly the rabbit hole we're jumping down in this deep dive. Today, we have a stack of notes, all centered around a dense, incredibly fascinating mathematical paper by PEDRO TEIXEIRA YAGO.
It's titled Hierarchies of Direct Powers, Ultrapowers, and Cumulative Powers.
Yeah, that's the one. And our mission here is to show you, the listener, how changing just one fundamental definition, what it means for two things to be the same, can take an infinitely complex, towering hierarchy of functions and instantly collapse it into a flat plane.
Or, conversely, if you turn the dial the other way, how it organically spawns one of the most mind-bending landscapes in all of mathematics.
A space so vast, it is literally called surreal.
Exactly, because it's a profound exploration of model theory. Yago isn't just, playing with numbers here. He's analyzing the architecture of logic itself.
Right.
He's asking, when you build massive, towering mathematical structures, what basic logical truths actually survive that construction process?
So to understand how the math breaks and how we eventually fix it to create these surreal numbers, we really have to understand how this skyscraper is built in the first place.
We do.
The paper starts with something called functional constructions. It's basically a way of building new mathematical spaces out of old ones.
Right, and Yago grounds us with a classic concept before he starts bending the rules. We need to look at what he calls a direct power.
Okay, I want to make sure I have the mechanics of this right before things get too weird.
Sure. The foundation is actually quite intuitive. You start with a set of numbers you're already comfortable with.
Like the base set math bn, the natural numbers.
Exactly. 0, 1, 2, 3, and so on. We consider this our base structure, or level 0.
Level 0, got it.
Now, we want to build a new space, level 1, made entirely of functions. To do this, you introduce an index set.
Let's ground that index set for a second. Instead of just calling it some abstract I, let's say our index set is the days of the week, Monday, Tuesday, Wednesday.
That works perfectly. So a function in this new level 1 space takes a day of the week as an input, and it spits out a natural number from our level 0 base.
So I might have a function that outputs the temperature for that given day. Monday is 70, Tuesday is 72, Wednesday is 68.
Precisely. The direct power is the massive collection of every single possible function that can map those days to those natural numbers.
Okay, so level 0 is just numbers. Level 1 is this massive library of functions mapping days to numbers. Now, if I'm operating on level 1 and I want to add two of these functions together, how does the math actually happen?
Because you aren't adding numbers anymore, you're adding whole temperature maps.
Exactly.
Well, the beauty of a direct power is that operations happen point-wise. You don't need new crazy rules for addition.
Lines-wise.
Yeah.
Hmm.
If you want to add function A and function B together, you just look at a specific point, let's say Monday. You take what function A outputs on Monday, you take what function B outputs on Monday, and you add those two base numbers together using the normal level 0 rules.
So it's like overlaying two spreadsheets.
Exactly like that.
You just add cell A1 to cell A1, B1 to B1. The operations on the higher level are completely dependent on and perfectly mirror the operations on the base level.
And you can keep building. You can take level 1, introduce a new index set, and build level 2, which consists of functions that output level 1 function.
Oh, okay.
You can build this tower up to infinity. But there's a very strict architectural rule here. Direct powers are non-cumulative.
Meaning the floors of the skyscraper are completely sealed off from one another.
Yes. The numbers live exclusively on level 0. The functions live exclusively on level 1. The higher order functions live exclusively on level 2.
So if you're standing on level 50, you are only dealing with level 50 objects. You cannot directly interact with a base number from level 0.
Right. The geometry of the structure simply does not allow it.
And this is where Yago throws a wrench into the architecture. This is like the core innovation of the paper.
Yep. The cumulative power.
He introduces the cumulative power. He asks what happens if we rip out those sealed floors. In a cumulative power, when you build level 1, you don't just put the new functions there.
No, you explicitly bring all the elements from level 0 up with you.
You retain the history. Level 0 is the base numbers. Level 1 contains all those index map functions, plus the base numbers themselves.
Right. And level 2 contains the higher order functions, plus the level 1 functions, plus the base numbers. They all share the exact same structural space.
But wait, my spreadsheet analogy completely breaks down here.
How so?
Well, in the sealed-off direct power, I knew how to add things because I was always adding a spreadsheet to a spreadsheet or a number to a number.
Ah, I see what you mean.
But in this new cumulative universe, if everything is living in the same room, someone could walk up and ask me to add a level 2 function directly to a level 0 base number. That shouldn't be mathematically possible.
It definitely seems like a contradiction.
A base number, like the number 3, doesn't take inputs, doesn't have a Monday. So how can I add it to a function that relies on inputs?
This was the major technical hurdle Yago had to solve. How do you force objects with fundamentally different types or geometries to interact organically?
Yeah, how does he do it?
To do this, he engineered a mechanism called the hereditary function var theta theta. Think of the Greek letter var theta theta as an automatic, universal translator that constantly runs in the background of this mathematical universe.
I need to see the gears turning on this translator. Let's say I'm forced to do exactly what I just described. I have a level 2 object, some complex function, and I have a level 0 object, the number 3. I want to add them together in this cumulative space. What is this translator actually doing?
The very first thing the system does when confronted with this addition is check the hierarchy. It asks, what is the highest level between these two objects?
Okay, so my function is level 2, my number is level 0, the maximum is level 2.
Right. So the system dictates that this entire addition must take place on the turf of level 2.
The highest ranking object sets the rules of engagement.
Precisely. Now, your level 2 function is already a level 2 object, so it's ready. but the base number 3 is stuck in the format of level 0. It's naked.
It's just a raw number.
This is why the hereditary function var theta swoops in. It reaches down, grabs the number 3, and forces it to behave like a level 2 object.
Wow.
It does this by wrapping it in a disguise. It turns the base number into a constant function.
Ah, so instead of being just the raw concept of 3, it stretches it out. If we go into the days of the week, it turns 3 into a function that just shouts 3 on Monday, 3 on Tuesday, 3 on Wednesday.
Yes. No matter what input you feed it, it returns 3.
You've captured the exact mechanism.
Mm-hmm.
By treating the lower level element as a constant function across the higher level index, it artificially inflates it so that pointwise addition works again.
You can now add your complex level 2 function to this new artificially constant function.
The paper actually walks through a specific highly detailed calculation of this in section 2.1, and tracing it really grounds how weird this gets.
It's a great example.
Let's unpack that for you. We are inside the cumulative structure of the natural numbers up at level 2, and we are told to add 2 very specific things. The first is our level 0 base number, the number 3.
And the second object is the level 2 successor function S1 S sub 1. This is a higher order version of a successor function.
The standard successor function just adds 1, right? Like the successor to 5 is 6.
Right.
But this is the function S1 S sub 1. It lives on level 2.
Yeah.
So its inputs aren't numbers, its inputs are other functions from level 1.
Yes. The rule Yago sets for it is dynamic. If you feed it a base number, it acts like a normal successor and just adds 1.
Okay.
But if you feed it a level 1 function, it goes into that function and applies the successor rule to every single output.
Let's visualize that.
Yeah.
Imagine a level 1 function as an infinite column of numbers. Let's say it's a function that just outputs odd numbers, 1, 3, 5, 7, and so on down the column.
Okay, I'm picturing it.
If I feed that entire column into the function S1 S sub 1, it goes through and adds 1 to every single slot. The 1 becomes 2, the 3 becomes 4, the 5 becomes 6.
So it transforms the odd number column into an even number column, 2, 4, 6, 8.
Right. That is the behavior of our higher order successor. Now the grand challenge. We need to calculate this dynamic level 2 function plus a static level 0 number.
Based on the translator rules, the maximum level is 2. So we have to build a new level 2 function. Let's call the answer result function.
To know what result function does, we have to feed it a test input. Let's feed it that same odd number column, 1, 3, 5, 7.
So the system evaluates both pieces at that input. First, the successor function evaluates the odd number column. As we just established, it outputs the even number column, 2, 4, 6, 8.
And now we evaluate the second piece. We evaluate the number 3 at that same input.
But because our translator has turned 3 into a constant function, it doesn't care about the input. It ignores the odd numbers completely.
It just outputs 3, but it outputs 3 for every single slot in the column.
The final step is to add them together pointwise, using the rules of the level below. You take your 2, 4, 6, 8 column, and to every single slot, you add 3.
The 2 becomes 5, the 4 becomes 7, the 6 becomes 9. Your final output column is 5, 7, 9, 11, and so on.
This is a brilliant piece of mathematical engineering.
It's like building a bizarre corporate hierarchy.
A corporate hierarchy.
Yeah. Think about it. In the sealed-off direct power company, the executives only talk to executives. The middle managers only talk to middle managers.
Right.
But in this cumulative company, a level 2 executive, our successor function, is forced to collaborate directly with a level 0 intern, our number 3.
I love this analogy.
They don't speak the same language. The executive speaks in massive workflow pipelines. The intern just holds a single piece of paper with a number 3 on it.
And the hereditary function var theta acts as the automated corporate translation software.
Yes. Whenever the executive demands input from the intern, the software intercepts the intern's single piece of paper, runs to the copier, prints out a billion copies of the number 3, and staples 1 to every single file on the executive's desk.
That's hilarious, but highly accurate.
The executive just sees a perfectly formatted, constant stream of data, and the pipeline keeps flowing.
That analogy perfectly highlights the semantic conservatism of the translator. It preserves the original meaning of the lower-level object, its 3-ness, but stretches its geometry so it can participate in higher-dimensional operations.
Right.
Yago proves that through this recursive mechanism, you can create an infinitely towering, completely interconnected mathematical universe where any object from any floor can be added, multiplied, or compared to any other object.
So we've successfully built the skyscraper. It's huge. It's highly interactive. Everything is talking to everything else.
Yep.
But anytime you build a new universe in model theory, the very next question is always about preservation. Do the fundamental laws of physics still work in this new building?
That is the big question.
If I have a basic mathematical truth on the ground floor, like, x plus y equals y plus x, does that truth survive the journey up to the 100th floor?
This is the central obsession of model theorists. When you transform a structure, what first-order logic sentences remain true?
First-order logic sentences.
Yeah, a first-order logic sentence is just a formal, symbolic way of stating a rule or a property. We actually have historical precedents for this.
Oh, we do.
In the mid-20th century, a mathematician named Alfred Horn proved that standard, sealed-off direct products preserve a specific class of logical formulas, which we now call Horn sentences.
Let's unpack Horn sentences briefly so we aren't just dropping names for the audience. What makes a Horn sentence special?
They are logical formulas constrained by a very specific limitation on how many positive assertions they can make in a given clause.
Okay, got it.
Later, Joseph Weinstein expanded on this by providing a highly rigorous syntactic characterization of the exact fragment of logic that direct powers preserve. Model theory has a very clear map of what truths survive in a non-cumulative world.
So in a standard direct power, Weinstein's specific fragment of logic survives. But Yago has built something entirely new here. He built a cumulative power with this automated translator running everywhere. Does it preserve the same logic? Does the math survive?
It does not.
Wait, really?
The cumulative power introduces a massive disruption. Yago's paper reveals that cumulative powers only preserve a highly restricted fragment of logic. They preserve what he defines as non-collapsible direct power sentences.
Non-collapsible. That implies that some mathematical truths are literally collapsing under the weight of this tower. What is doing the collapsing? I thought our translator fixed all the interaction problems.
Well, it fixed the operations, it fixed addition and multiplication, but the culprit causing the collapse is the equal sign itself.
The equals sign.
Yeah, there is an incredible asymmetry built into the foundation of Yago's universe. Operations and relations are defined hereditarily. They use the translator to reach back and figure things out. But equality is defined as strict absolute identity.
Wait, slow down. Strict absolute identity. Are you saying that in this universe, if I want to know if two things are equal, the translator doesn't help me?
The system does not use it for equality. For two objects to be considered equal, they must be the exact, identically same structural object living in the exact same set.
Oh, what?
Even if they behave identically in every possible operation, if their mathematical DNA is different, if one is a function and one is a base number, they are declared unequal.
We need an example of this because this is where the mind bending starts. Show me a truth that collapses. The paper uses a brilliantly simple arithmetic example with level 1 of the natural numbers.
Let's look at it. Consider a basic, undeniable truth of integer arithmetic. The arithmetic equation 3 plus minus 1 equals 2 plus negative 1 equals 2.
On level 0, the ground floor, this is an absolute truth.
Right. Now, let's take this equation up to level 1. We're now dealing with constant functions.
Yeah.
Let's take the constant function that always outputs 3 and add it to the constant function that always outputs minus 1.
We know how this works. It's pointwise addition. For every single input, the system calculates 3 minus 1 and it outputs 2. So the result of that addition is a new constant function that always, without fail, outputs the number 2.
The behavior of that resulting function is perfectly identical to the concept of 2. It will never give you anything else. But remember the strict rule for equality.
Right, strict identity.
We have a sentence that asks, does the result of this addition equal the base number 2? The result of the addition is a level 1 object. It is a function. The base number 2 is a level 0 object. It is an integer.
Oh. Even though the function screams 2 at every conceivable point in the universe, it is technically a function. The other thing is a number.
Exactly. So when the system's logic checker looks at the sentence, it sees a function on one side of the equal sign and an integer on the other. It checks for strict structural identity. They are different object types.
So it just breaks.
The equal sign shatters. The equation 3 plus minus 1 equals 2 plus negative 1 equals 2 is evaluated as false in the cumulative power.
This is the 2 not equal to 2 scenario we opened with. The math is actually working perfectly. The addition isn't broken. The function is outputting 2.
Exactly.
The system is failing because the definition of equals is entirely too pedantic. It's like Having a physical paperback copy of Moby Dick in one hand and a Kindle displaying the exact same text of Moby Dick in the other hand.
That's a perfect way to look at it.
If I ask a normal person, are these the same book? They say yes. But if I ask Yago's strict equality checker, it says, absolutely not. One is made of paper and ink, the other is made of plastic and pixels. They are fundamentally unequal.
The media format prevents the identity. Any logical sentence that tries to assert positive equality between objects that might behave the same but originate from different levels of the hierarchy will collapse.
Which is why he calls them collapsible sentences.
Right. They attempt to force the hierarchy to compress itself into a single identity, and the strict rules reject it.
So only sentences that carefully avoid relying on cross-level identity, the non-collapsible ones, survive the journey up the tower.
Yago's theorems formalize this, but, this leaves us in a really awkward spot, mathematically speaking. We built this gorgeous interactive universe, but because our building inspector, the equal sign, is a fanatic about structural identity, basic arithmetic is being declared false.
Yep.
How do we fix this? Can we fire the building inspector and change the definition of equality? We can, and that is precisely the pivot the paper makes. We need to introduce blurriness.
Blurriness.
Yes. We need to force the mathematical universe to stop caring about what things are made of and only care about how they behave. We do this by applying what mathematicians call an equivalence relation.
An equivalence relation. It's a way of mathematically stating, I know these aren't strictly identical, but I am legally declaring them equivalent for all future calculations. How does Yago define this new blurry equality?
He defines it hereditarily, using our old friend, the hereditary function var theta.
The translator is back.
He creates a new rule. Two objects in this cumulative tower are considered equivalent if, when you use the translator to trace them all the way down to their base interactions, the resulting outputs are the same.
We are finally letting the translator handle the equal sign. So going back to the Moby Dick analogy, under the new hereditary equivalence rule, the system doesn't look at the paper or the plastic.
No, it doesn't.
It uses the translator to literally read the words. It reads the first page of the paperback. It reads the first page of the Kindle. Call me Ishmael. The behavior is identical. So the system slaps a stamp on them that says equivalent.
And once you establish that equivalence relation, you can perform a mathematical operation called quotienting.
Let's make sure that's clear for you listening. Quotienting is basically grouping. You take everything that has that equivalent stamp, you throw them all into a bucket, and you treat that entire bucket as a single new mathematical object. You blur them together.
Yes, and when you quotient Yago's complex, multi-level cumulative tower by this hereditary equality, the results are spectacular. The moment you declare that a constant function of 2 is legally identical to the base number 2, all the cross-level distinctions vanish. The intern and the executive, if they are producing the exact same spreadsheet, are fused into a single entity.
The tower collapses.
It completely flattens. Theorem 3.6 of the paper proves this definitively. When you quotient the cumulative power by hereditary equality, the resulting structure is perfectly isomorphic to meaning structurally indistinguishable from a standard, sealed-off direct power.
That is a staggering realization.
Yeah.
The only thing separating this infinitely complex, interactive multiverse from a standard, boring, flat structure was the strictness of the equal sign.
Exactly.
The moment you allow behavioral equivalence, the complexity evaporates. It reveals that the cumulative power is basically just a stretched-out, uncompressed version of a direct power.
The cumulative power is the raw, untethered maximum complexity, and equivalence relations are the tools you use to carve specific realities out of it.
Right.
Because Yago doesn't stop there. He asks the deeper question. If blurring the lines based on absolute 100% perfect agreement collapses the tower, what happens if we blur the lines even further? What if we don't demand perfect agreement?
Oh, this is where we get into wild stuff. What does less than perfect agreement mean in math? If two functions agree on Monday and Tuesday, but disagree on Wednesday, are they equal?
In a finite set, like the days of the week, you could just go with majority rule. But remember, our index sets can be infinite.
Oh, right.
What if you have two functions and they agree on an infinite number of points, but they also disagree on an infinite number of points? Which infinity wins?
That's a huge problem.
To answer this, model theory uses a concept called an ultrafilter.
An ultrafilter. I've seen this term described basically as a voting system for infinity. But how does a mathematical voting system actually work? Infinity doesn't have a distinct shape. How does an ultrafilter choose which infinite pile of numbers wins? I'm not really seeing the mechanism here.
It is deeply counterintuitive. Think of an ultrafilter as a preordained list of winning coalitions. You look at your index set, let's say all the integers. An ultrafilter is a strict set of rules that definitively categorizes every single possible subset of those integers as either large, meaning it matters, or small, meaning it is negligible.
It's gerrymandering infinity. You are drawing abstract district lines through an infinite space and declaring ahead of time which districts have the power to decide the truth.
That is exactly what it is. And the rules of an ultrafilter are rigid. For instance, if a subset is declared large, its complement, everything outside of it must be declared small. There are no ties.
No ties allowed.
So let's go back to our two functions, function A and function B. You want to know if they are equal under this ultrafilter. You look at every single input where function A perfectly matches function B. You gather all those matching points into a subset.
Okay, I have my pile of matching points.
Now, you hold that subset up to the ultrafilter. Does the ultrafilter consider this specific subset large? If the answer is yes, then congratulations. Function A and function B are declared mathematically equal in this universe.
Wow.
It does not matter if they disagree on 10 trillion other points. If the ultrafilter says the matching points belong to the winning coalition, the disagreements are entirely ignored. They are erased from the mathematical reality.
That is aggressively blurry. You are aggressively forcing consensus. So what happens to Yago's cumulative skyscraper when we quotient it by this ultrafilter? We apply this intense gerrymandered voting system to the whole structure.
You generate a structure known as an ultrapower. And ultrapowers are the holy grail of preservation in model theory, thanks to something called Usch theorem.
Usch theorem.
Yes. It guarantees that an ultrapower will perfectly preserve every single first-order logic sentence of the original base structure.
Wait, every sentence. Earlier, the cumulative power was breaking basic arithmetic because of strict equality. The direct power only preserved horn sentences. But by applying an ultrafilter, by being incredibly loose and gerrymandered with our definition of equality, we suddenly preserve absolutely everything. Why? How does making the math blurrier make the truth stronger?
Because the ultrafilter bypasses the noise of identity. Remember why the math broke earlier?
Yeah, because one was a function and the other was a number.
Exactly. It broke because the system got caught up on the object types. But the ultrafilter doesn't care about object types. It only cares about the set of points where behaviors align.
Right.
If the behavior aligns on a large set, the ultrafilter forces the system to treat them as identical. By ignoring isolated disagreements and forcing consensus based on these large sets, Usch's theorem proves that the entire logical structure of the base level is smoothly, flawlessly projected up into the infinite hierarchy.
The truth is maintained because the ultrafilter paves over the structural contradictions.
Precisely.
Yeah.
Now, Yago starts exploring the relationships between these ultrapowers, and there's a specific term in the paper I want to unpack: embeddability. He looks at whether one ultrapower can fit inside another.
Yes. If you have structure A and structure B, and you already know that structure A can be perfectly embedded, meaning a pristine, exact copy of it exists inside structure B.
Right.
The question is, if I build an ultrapower out of A and an ultrapower out of B, does the embeddability survive? Will ultrapower A fit perfectly inside ultrapower B?
And the paper says this only works if the ultrafilters follow the relation less than or equal to RK, also known as the Redefining ordering.
Which sounds incredibly intimidating.
Yeah.
What does it mean for one infinite voting system to be less than or equal to another voting system?
The Redefining ordering is essentially a way of measuring the fineness or the dominance of different ultrafilters. Remember, there isn't just one way to gerrymander infinity. There are countless different ultrafilters you can define. Some are very blunt, some are incredibly intricate. If ultrafilter X is less than or equal to ultrafilter Y in the Redefining ordering, it roughly means that the voting rules of Y are capable of perfectly simulating the voting rules of XY is a more dominant, finer filter.
So Yago proves that the architecture is maintained. Ultrapower A embeds into ultrapower B if and only if the voting system used for A can be simulated by the voting system used for B. The hierarchy of the filters dictates the geometry of the universes they create.
It's a profound unification. The cumulative power is a raw, unedited multiverse of all possible functions. It's the marble.
Okay, I like that visual.
If you use a chisel called strict identity, you get a broken structure where basic math fails. If you use a chisel called hereditary equivalence, you carve out a direct power. If you use a chisel called an ultrafilter, you carve out a truth-preserving ultrapower. The rules of sameness generate the shape of reality.
We've learned how to build the tower. We've learned how to use equivalence relations and ultrafilters to collapse it into different shapes. But mathematics rarely stops at finite exercises. Every time a mathematician builds a machine, the very next thing they do is turn the dial to infinity and see if the machine explodes.
They absolutely do.
What happens if we take this entire process, building cumulative layers, filtering them with an ultrafilter, preserving the truth, and we iterate it infinitely? What is waiting at the end of the line?
This is the climax of Yago's paper, deep in Section 5. He moves beyond building level 1, level 2, or even level 100. He explores what happens when you iterate this ultrapower construction over transfinite ordinals.
Transfinite ordinals. We need to define that for you, the listener. We aren't just saying it goes to infinity. An ordinal is a way of counting the order of things, first, second, third.
Right.
Transfinite ordinals are what happen when you finish counting to infinity, and then you just keep counting. Infinity plus 1, infinity plus 2. We are pushing this structural tower through different expanding sizes of infinity.
Exactly. We are pushing the hierarchy to an absolute limit. But to survive this journey, you cannot start with a flimsy foundation. You can't just start with the natural numbers.
No.
To reach the ultimate limit, Yago dictates that we must start with the saturated structure état état set.
Okay, the saturated structure état état set. What makes that different from a normal set of numbers?
It is deeply, intensely saturated. Think of the standard real numbers, every decimal you can imagine. Between any two real numbers, no matter how microscopically close they are, you can always find another real number.
Right.
An état set takes this density to a structural extreme. It lacks any endpoints, and it is universally dense. A classic example in this context is a real closed field, like the hyperreal numbers. It is a foundation that already contains a dizzying amount of infinity.
Okay, so we have this massive saturated foundation. We start building our cumulative tower on top of it. But we don't just use any random ultrafilter to collapse the levels as we go up. Yago's very specific here. He says we have to use Tails ultrafilter.
Tails ultrafilters, yes.
Why the tail? What makes a Tails ultrafilter special?
It comes back to how we gerrymandered the voting system. A Tails filter is an ultrafilter that explicitly despises the finite. It dictates that any finite subset, no matter how large, is automatically categorized as small and negligible.
Wow, okay.
The only sets of points that are considered large enough to dictate truth and equality are the ones that stretch out infinitely toward the end of an ordering. There are the infinite tails of a sequence.
So a Tails ultrafilter is a voting system that only values ultimate, long-term, asymptotic behavior. It doesn't care what two functions do for the first billion, trillion, or quadrillion steps.
Yeah.
It only cares if they eventually agree forever at the edge of infinity.
Yes. It is a filter of ultimate destiny. So picture the mechanism. You start with an intensely dense état état set. You build a cumulative layer. You filter it using ultimate destiny.
Okay.
You build the next transfinite layer. You filter it again. You do this forever across the class of all ordinals. As you approach this ultimate limit, something magical happens. The structure begins to absorb everything in mathematics.
What do you mean, absorb everything?
Theorem 5.1 and corollary 5.32 lay out the final revelation. This requires a foundational assumption in set theory called global choice, which essentially guarantees that we can consistently make selections across these massive infinite classes.
Right.
If you assume global choice and you push this iterated, tail-filtered hierarchy to the absolute limit, the resulting structure achieves two properties. First, it is maximally saturated. Second, it is universally embedding.
Universally embedding, meaning every single possible ordered field, no matter how large, how complex, or how bizarre, can find a perfect, intact home inside this final structure.
Everything fits inside it. It is the absolute maximum continuum. And Yago points out that this structure, generated purely through model theory and cumulative ultrapowers, is fundamentally isomorphic to something very famous and very strange in mathematics.
It naturally spawns Conway's surreal numbers.
It is perfectly isomorphic to the surreal field.
For you listening, if you haven't encountered John Conway's surreal numbers, they're one of the most beautiful concepts in math. Standard real numbers have conceptual gaps, but the surreal numbers are an unimaginably vast, totally unbroken continuum.
They contain all the integers, all the fractions, all the irrationals like pi.
But they also contain infinities. Not just one infinity, but a whole spectrum of numbers infinitely larger than infinity. And even wilder, they contain infinitesimals numbers that are greater than 0, but infinitely smaller than any standard decimal could ever express. They fill every conceivable mathematical gap.
It is the ultimate number system. Conway originally discovered them by analyzing combinatorial games, literally studying the mathematics of playing games like Go.
Right. He found them looking at game theory. But what Yago has proven here is an entirely new, deeply structural pathway to generate them. Let's synthesize exactly what that means, because this is the massive aha moment.
Go for it.
We started this deep dive looking at basic functions, spreadsheets mapping days of the week to temperatures. We stacked them up, but we made a simple rule change. Keep the old floors around.
The cumulative power.
Right. Then, because the strict definition of equality kept breaking our arithmetic, we introduced an ultrafilter, a gerrymandered voting system, to force consensus based only on the ultimate infinite tails of behavior.
Yes.
By endlessly stacking and heavily filtering these basic functions across the transfinite infinite, the math organically blooms. It expands and solidifies into the surreal numbers. It's like we started with a single basic brick, we applied a very specific weird rule for how to blur the mortar between the bricks, and we accidentally constructed a hyperdimensional megacity that contains every single architectural blueprint that can possibly exist in the universe.
It is a stunning demonstration of generation through constraint. The surreal field isn't just a bizarre, isolated quirk of game theory. Yago shows us that it is the natural, inevitable mathematical limit of iterating filtered cumulative hierarchies. It is exactly what happens when you push functional complexity and behavioral equivalence to the absolute edge of infinity.
It fundamentally changes how you view complexity. And bringing this massive infinite cosmos down to a core takeaway for you, I think this paper is a masterclass in the philosophy of boundaries. It demonstrates that you do not need infinitely complex, labyrinthine rules to generate a universe-encompassing system.
You really don't. The complexity of the surreal field emerges entirely from the interaction of a simple, cumulative build process and a rigorous, tweakable definition of equivalence.
Exactly. The power isn't in the objects. The power is in the boundaries between the objects. And that brings me back to the rigid, sealed-off skyscraper we started with. Yago's paper mathematically proves that if you simply change the definition of equality, if you relax your strictness and allow things that behave the same to be treated as the same, an infinite, overwhelming hierarchy instantly collapses into a flat, clean, perfectly functional plane.
It makes you wonder, doesn't it?
It really does. Step outside of abstract math for a second. Look at our own lives. Look at our social structures, our legal systems, our massive corporate organizations.
The human hierarchies.
Right. How many massive, complex, bureaucratic human hierarchies only exist because we are using an overly strict, pedantic definition of sameness? How much friction in our world is caused by us staring at a physical book and a digital book and declaring they are entirely different instead of just reading the text?
If you change the filter, you change the universe.
If we changed our filter, if we focused on ultimate behavior instead of strict identity, what else in our world might suddenly collapse into something beautifully simple? Well, thanks for diving into the architecture of infinity with us today. Keep questioning the boundaries and keep exploring the structures around you.
You know, usually when we talk about a mathematical structure, there is this underlying expectation of like flat, pristine precision. Think about building a massive suburban subdivision for a second.
Like a grid.
Yeah, exactly. A grid. You map out the plots, you build identical houses on each plot, and the surveyor just points and says, there it is, an infinite grid of the exact same thing. Everything has its place, everything is strictly parallel, and, well, nothing overlaps.
It is very horizontal. It is clean. I mean, in algebraic model theory, we really love that kind of predictability. We like to take a mathematical object and just clone it infinitely across a flat plane.
And it is deeply comforting, you know. We like things to be safely categorized on a single plane of existence. But today, for this deep dive, we are looking at a structural landscape that takes that flat suburban grid and realizes it is completely inadequate for the kind of universe we actually want to build.
Inadequate is putting it mildly.
Seriously. Instead of a flat grid, we are looking at an architecture that is honestly like an impossibly tall, infinite skyscraper. And here is the mind-bending part. Every single new floor of this skyscraper somehow contains the blueprints, the raw materials, and the living inhabitants of every single floor below it.
It is the absolute definition of a layered transfinite multiverse.
Exactly. So, welcome. I am so glad you were joining us today. We are going to deconstruct how a recent paper in mathematical logic uses this exact towering architecture to synthesize the largest numbers mathematically possible. And I need to be upfront with you. We are operating under the unabridged protocol today.
Which means we're not skipping a single floor on the way up. Time is an illusion here.
Right. We have all the time in the world. We will not skip a single paragraph, formula, or logical deduction. The paper is Hierarchies of Direct Powers, Ultrapowers, and Cumulative Powers by PEDRO TEIXEIRA YAGO. Our mission today is an exhaustive, line-by-line deconstruction of how you build this skyscraper, how you do math inside it, and ultimately how it creates a universe of numbers that is so vast, it almost breaks the boundaries of standard set theory.
I think the best way to set the expectation right now is that we're going to deconstruct not just the what of this paper, but the why. Mathematical logic at this level can feel like staring at a wall of arcane runes.
Oh, totally.
But every single structural choice the author makes, every time they redefine what it means for two things to be equal or what it means to add two objects together, is serving a massive strategic goal.
Let us start right at the title then. Hierarchies of direct powers, ultrapowers, and cumulative powers. We have three main concepts here: direct powers, ultrapowers, and cumulative powers.
Let us slow down and do a foundational digression right here on the title. What does a power, specifically a direct power, actually mean in algebraic model theory?
Yeah, what is the baseline?
Basically, it means taking a base object, like the integers, and creating a massive function space from it. You are multiplying the structure by itself across an index set. And an ultrapower takes that massive function space and quotients it. It blurs it down using a very specific mathematical filter called an ultrafilter.
Okay, so that sets up the three pillars. That covers the title. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the abstract.
Perfect. So looking at the first paragraph of the abstract, the paper states it is investigating cumulative hierarchies of functions. It talks about comparing these to standard direct powers and ultrapowers.
Right, and it mentions characterizing the fragment of first-order theory it preserves. That is the huge why for this paper.
Let me throw out an analogy for this. Think of standard direct powers as a flat multiverse where parallel timelines exist, but they just do not interact, whereas these cumulative powers are like a layered multiverse. Higher dimensions actually contain and interact with the original lower dimensions.
That is a great way to visualize it.
Mm.
And the reason the author wants to characterize the fragment of first-order theory it preserves is because when you smash all these dimensions together, you risk breaking the logical rules. They need to figure out exactly which mathematical truths survive the transition from the flat grid to the infinite skyscraper.
That covers the first half of the abstract. Have we missed any nuances?
I think we thoroughly unpacked it. Let's proceed to the second half of the abstract.
Okay, the second half of the abstract drops the final hook. It says the ultimate application of this framework is constructing a surreal field.
Yes, the synthesis of John Horton Conway's surreal number.
I really want to push back on this for a second, because why do we care about a surreal field? What actually is it? And why is reaching it via cumulative power such a massive payoff?
To understand the surreal numbers, you have to understand that they are, without exaggeration, the absolute largest possible ordered field in mathematics. Conway actually discovered them almost by accident in the 1970s while he was analyzing endgames in the board game Go.
Wait, really? He built a foundational number system out of game theory?
Essentially, yes. In the surreal framework, a number is defined entirely by two sets of previously created surreal numbers, a left set and a right set. The new number is simply the simplest possible value that sits strictly between the left set and the right set.
So it is built on options.
Exactly. And you build this universe transfinitely, day by day. On day 0, you start with nothing. The left set is empty. The right set is empty. The simplest number between nothing and nothing is 0. So 0 is born.
Okay, so on day 0, we just have 0. That makes sense.
Right. Then on day 1, you use 0. You put 0 in the left set and nothing in the right set, which creates the number 1. Put 0 in the right set and nothing in the left, you get -1. By day infinity, the first infinite ordinal, you have generated every single integer, every fraction, and you start filling in all the real numbers like pi.
But the real numbers are already infinitely dense. Where do you possibly go after you have all the real numbers?
That is where the surreal field earns its name. You just don't stop. You go to day infinity plus 1, you take the entire infinite set of real numbers, put them in the left set, and put nothing in the right set.
Oh, wow.
Yeah. The number born from that is strictly greater than every real number. It is an infinitely large number. And simultaneously, you start creating infinitely small numbers, infinitesimals that sit nestled delicately between 0 and the smallest real fractions.
So the surreal field contains literally everything. The reals, the hyperreals, the ordinals. It is the absolute limit of math. And this paper claims to build it using our transfinite skyscraper. That covers the abstract. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the introduction.
Awesome. Moving to paragraph 1 of the introduction, the text states that functional constructions like direct powers and ultrapowers are essentially non-cumulative. Let us unpack that rigorously.
Sure. This goes back to the flat grid. If we have a base mathematical structure, like the standard integers, a direct power blows that reality up into a massive parallel function space. You have an index set, which is like a vast collection of distinct parallel timelines.
Okay, so timeline 1, timeline 2, timeline 3, going on forever.
Exactly. The direct power is simply the set of all possible functions that map those timelines back into our base reality of integers. So one element is a function saying, in timeline 1, my value is 5, in timeline 2, my value is 10.
But the author says this is non-cumulative. Why? Because the original integers do not interact with the new functions, right?
Precisely. There is a trivial embedding, sure. You can pretend the integer 5 is in the new space by calling it a constant function that just outputs 5 in every timeline. But there is no direct interaction between the generating structure and the resulting ones. They are isolated ontological floors.
That covers the first paragraph of the introduction. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next paragraph.
Okay, paragraph 2. The math protocol officially begins here. The author introduces functions from an index set U into the naturals. The collection of functions is non-Delaunay to the power I.
And we need to explain how you do math in this Dan-Delaunay to the power I space. You do it point-wisely. It is completely horizontal parallel computing. The equation is 5 off 1, death row men, equals or G, FF rhyme of F1 through F dan equals G.
Let us do a foundational digression on that. What does that equation actually mean for someone trying to add two functions?
It means that if you want to apply an operation like addition to a bunch of functions, you just go down the line. For every single timeline index, you add the outputs of those functions together to get the output of the new function G. It only works if every input is a function.
Right. And then the text talks about extending this. It introduces the transfinite extension, denoted as alina-bolina, over an ordinal class. Why transfinite induction? What even are ordinals in this context?
Ordinals are essentially a way to count beyond infinity. When you build these function spaces, you do not have to stop at step 2 or step 3. You can go to step infinity, which is the first limit ordinal, and then keep going to infinity plus 1. Transfinite induction is the logical engine that allows you to prove things are true across this endless, towering sequence of construction steps.
That covers paragraph 2. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to paragraph 3.
Paragraph 3 is the massive shift. We move to cumulative powers. The cumulative step is n beta plus n beta plus equals n sub beta to the power of I sub beta union n sub beta.
That union operator changes the entire universe. We're not just taking the function space anymore, we are physically dumping all the raw elements from the previous floor directly into the new floor. Floor 1 contains complex functions, and D, it contains the raw integers from floor 0.
And they are coexisting in the exact same mathematical space. But the author uses the phrase semantically conservative. Why can't operations be pointwisely defined anymore?
Because elements from different levels are now mixing. If you were to pointwisely add a raw integer to a transfinite function, the math just crashes. The operation asks the integer for its output in timeline 2, and the integer just stares blankly. It is a number, not a mapping.
So the whole parallel computing grid collapses. That covers paragraph 3. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to paragraph 4.
Paragraph 4 outlines the 4 interconnected goals of the paper. First, defining the cumulative framework. Second, relating it to direct powers and ultrapowers. Third, lifting embeddability between these structures. And fourth, the surreal field application.
It is a very clean, ambitious roadmap for the rest of the text. They're going to build the skyscraper, figure out its shadows, see how they fit together, and then use it to build the ultimate number system.
That covers the introduction. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 2.
All right, section 2. This is the framework, the hereditary definition. We start with definition 2.1 and 2.2, which formally define the hierarchy and the levels. For the limit stages, the limit stage is lambda x, f sub lambda of x equals the union over alpha less than lambda of f sub alpha of x.
This just formalizes what we said earlier. At a limit floor, like floor infinity, you just take a massive union of every single thing built on the floors below it. But definition 2.2 is where it gets highly technical. It defines the level of an element, denoted by the Greek letter rho.
Okay, so why is tracking this level rho so crucial?
Because it determines how operations look back down the hierarchy. Since we have all these different objects mixing together, the universe needs to know exactly which floor an object was born on to know how to interact with it. The level row is basically the object's birth certificate.
That covers definition 2.1 and 2.2. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to definition 2.3.
Definition 2.3 is the heart of the entire paper. This is the core cumulative power hierarchy. First, I need to point out the signature. The signature is sigma vile, Arangel sigma equals the tuple of the family of functions f sub I, the family of relations r sub I, the family of constants c sub I, and the arity function ar.
That signature just tells us what tools we have to work with, our operations, our relations, our constants. But the most important part of this definition is the hereditary function, the Greek letter theta.
Yes, the theta function. Let us break down the why here. Why does theta even exist? What is its job?
Think of theta as an anchor, or like a highly intelligent translator. It forces higher level functions to look down to the exact ordinal level where an element was born to figure out how to evaluate it.
So if I try to add a complex function to a standard integer, theta steps in. Does it translate the integer into a constant function at the right level so they can interact?
Exactly. Let us say you are on floor 5. You have a complex function from floor 5, and you want to add it to a raw integer from floor 0. The addition operation needs an output for a specific timeline index. Theta looks at the integer and asks, were you born on floor 5? The integer says no.
Right, it was born on floor 0.
Now, theta wraps the raw integer in a protective bubble. It essentially says, I'm going to treat you as a constant function for this specific operation. It forces the operation to push down floor by floor until it hits the foundational level where the math actually makes sense.
That covers definition 2.3. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 2.1.
Section 2.1 provides a concrete example of this. The author walks us through adding an extended successor function called S1 and the raw integer 3 inside the second level of the hierarchy, F2 of n.
This is a beautiful line-by-line deconstruction opportunity. We are calculating S1 plus 3. The paper uses a matrix or column vector to represent S1 so the reader can visually see the math.
Let us trace that calculation for the listener auditorily. So S1 is a massive vertical list. The top half of the list handles raw integer inputs, and the bottom half handles function inputs.
Right, and we want to add the raw integer 3 to this entire massive vector. We are on floor 2. Theta looks at the 3, sees it was born on floor 0, and protects it. So we just try to add 3 to every single slot in the column vector.
The top slots are easy. It is just raw integers. 2 plus 3 is 5, 3 plus 3 is 6. But what about the bottom slots, the ones that contain arrays, like the sequence 2, 2, 6?
When the operation tries to add 3 to the array 2, 2, 6, it crashes. So theta intervenes again. It pushes the 3 down to floor 0 and evaluates the array point by point. 2 plus 3 is 5, 2 plus 3 is 5, 6 plus 3 is 9. The drop of ink seeks all the way down to the foundation.
It is stunning to visualize. That covers section 2.1. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 2.2.
Okay, section 2.2. Preservation and properties. We know how to build a universe now, but what logical rules actually survived the journey up the layers? The author introduces Horn formulas here. Let us do a foundational digression. What is a prenex conjunctive normal form, and what makes a formula a Horn formula?
In first-order logic, you can structure any sentence as a series of AND gates connecting groups of OR gates. That is your conjunctive normal form, like a checklist of requirements, and inside each requirement, you have multiple choice options.
Okay, so requirement 1, A and D requirement 2, and inside requirement 1, it is option A or option B.
Exactly. The individual options inside the OR gates are called literals. They can be positive, like x equals y, or negative, like x does not equal y. A Horn formula dictates that inside every single one of those multiple choice OR gates, there is at most one positive statement. All the other options must be negative.
Why does having mostly negative options matter?
Because of logical implication. If I want to say if A and B are true, then C is true, I can rewrite that as either A is false or B is false or RC is true. 2 negative statements, 1 positive statement. Horn formulas perfectly capture deterministic rules. And historically, Chang, Morel, and Keisler found that these specific deterministic sentences are preserved when you create proper reduced products.
That covers the introduction of Horn formulas. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to Weinstein's characterization.
The paper moves to direct powers via Weinstein's complex syntactic characterization in proposition 2.1. And we have a complex formula to read here. The logical structure is big V bigwidge exists, xn. the disjunction of the conjunction of there exists x sub n such that phi sub n.
Right. Joseph Michael Weinstein wanted to know what sentences are preserved by direct products, and he discovered this cascading architectural requirement. It is an alternating sequence of OR statements containing ND statements wrapped in their exist quantifiers and then flipping to for all quantifiers.
Why is the author looking at direct powers instead of reduced products here?
Because in our cumulative skyscraper, equality is strict identity. You are only equal to yourself. Because of that strict equality, cumulative powers handle truth much more like direct powers than reduced products. They need Weinstein's net to guarantee timeline by timeline truth.
That covers Weinstein's characterization. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to definition 2.16 and 2.17.
Definitions 2.16 and 2.17 introduce a brand new concept: a non-collapsible positive equality. I like to think of collapsible formulas as statements that accidentally force two different floors of our multi-story building to smash into each other.
That is exactly what they are. In our hierarchy, a function on floor 10 is fundamentally different from an integer on floor 0. If a sentence demands they are identical, the logic of the universe breaks. So the author outlines 3 clauses to guarantee inequality is safe.
The first 2 are about variable distribution. But the third clause is fascinating. It says an equality is safe if both sides are governed by existential quantifiers, but dangerous if governed by universal quantifiers. Why do existentials and universals behave so differently across hierarchy levels?
An existential quantifier. There exists an X gives you agency. You have the freedom to deliberately search a specific floor, find an object of the exact same rank, and declare that to be X. It prevents a collapse.
Right, you get to choose something that fits.
But a universal quantifier for all X is a brute force attack. It violently grabs every single object from every single infinite floor and forces it into the equation. It completely ignores structural rank, which forces the roof of the skyscraper to behave identically to the foundation. That destroys the whole point of building layers.
That covers definitions 2.16 and 2.17. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to corollary 2.27.
Corollary 2.27 is the ultimate payoff of this section. It states that finite cumulative powers preserve exactly non-collapsible direct power sentences, and arbitrary cumulative powers preserve constant-free, non-collapsible direct power sentences.
It is a gorgeous, airtight piece of logical boundary drawing. The author perfectly mapped the physics of this new transfinite universe. If you want a truth to survive the infinite climb, it must survive Weinstein's net, it must be non-collapsible, and if it goes to infinity, it cannot have constants, because dragging a constant up through infinite limit ordinals makes it lose its definitional anchor.
That covers corollary 2.27. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 3.
Okay, section 3. Direct powers and the hierarchy. Since cumulative powers act a bit weird with equality being strict physical identity, what happens if we forcefully twist the dials of reality and make equality hereditary?
We are moving from equality by physical identity to equality by behavioral inheritance.
Let us look at definitions 3.1 and 3.2. They define the direct power hierarchy and a new equivalence relation. The equivalence relation is Lopative beta plus B if known, Vardadal 1 is IDIP core 1, Fardal B is equivalent sub beta plus to B if and only if for all j and I sub delta minus 1, theta sub delta superscript j of A is equivalent sub delta minus 1 to theta sub delta superscript j of B.
This is a profound philosophical mathematical shift. This new rule says, to determine if object A is equivalent to object B, we call the theta function. We drag both objects all the way down to the foundational timelines. And we just look at their outputs.
Yeah.
If their outputs at the foundational level perfectly match, we declare them mathematically equivalent, regardless of what floor they were born on.
So quotienting the cumulative power by this specific equivalence relation perfectly reconstructs the direct power. Theorem 3.6 proves this. It means cumulative powers are the master template. The flat direct powers are just a restricted shadow of the skyscraper.
Yes, the flat grid is just an illusion caused by ignoring the origin of the objects.
That covers definitions 3.1 and 3.2. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 4.
Section 4 moves to ultrapowers and the hierarchy. If twisting the dial to behavioral inheritance gives us direct powers, we can twist it even further using ultrafilters. Definition 4.1 and proposition 4.3 define a new relation, tilde sub beta, using a family of ultrafilters U sub alpha.
We really need to define an ultrafilter clearly here. Why do we need it? Think of our timelines as a population of voters. An ultrafilter is a constitutional rulebook that decides which specific subsets of voters constitute a decisive majority.
And it is totally abstract, right? Not just 51%.
Right. It has strict rules. The whole population is a majority. An empty room is never a majority. The intersection of two majorities is a majority. But the defining ultra property is that for any subset of voters, either that subset is a majority or its exact complement is a majority. No ties allowed, ever.
So they use this voting system to define the equivalence relation tilde sub beta. They ask the timelines if object A and object B agree. If the set of timelines voting yes is considered a majority by the ultrafilter, the universe declares them mathematically equal.
Even if billions of timelines voted no, the ultrafilter forces a massive compression of the universe. The author adapts Ush's theorem to show this preserves first-order logic.
That covers definition 4.1 and proposition 4.3. Have we missed any nuances?
I think we thoroughly unpacked it. Let's proceed to theorem 4.20.
Theorem 4.12 brings up embeddability and the Redefining ordering. How do we lift embeddings between these massive voting structures? The Redefining ordering is would UI, UJU sub B, HO, U sub I is less than or equal to RKU sub J.
This ranking asks which voting systems are more complex. System J is more complex than System I if we can draw a perfect projection mapping between their districts. If the projected voters form a majority in J, the original group must be a majority in I.
And Theorem 4.0 proves an embedding exists between the ultrapowers if and only if their ultrafilters have this exact Redefining relationship.
And the proof is wild. They have to construct a mapping function H and prove it is multiplicative, additive, subtractive, and covering. Multiplicative preserves the AND gate, subtractive preserves the NOT gate. It rigorously guarantees that truth survives the translation across completely different voting universes.
That covers Theorem 4.31. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to Theorem 4.31.
Theorem 4.31 investigates when an ultrapower embeds backward into its corresponding direct power. I have major pushback on this. An ultrapower is usually way bigger or wildly different than a direct power. It creates infinitesimals. How can it embed back into it?
It is highly counterintuitive. To solve this, the author defines the support of a structure. The support looks at the bare minimum machinery required to keep the universe running. It calculates the maximum cardinality of the tuples needed to define the algebra.
And the author denotes this specific parameter as tau.
Exactly. And the author proves that to embed backward, the ultrafilter cannot be standard. The parameter is tau plus AIU, tau plus of A to the power of I modulo U. It must be tau plus complete.
Meaning, if you partition the voters into tau many groups, the ultrafilter aggressively selects exactly one group as the sole majority.
Yes, it is a terrifyingly strong constraint. It prevents the ultrapower universe from fracturing into bizarre new equivalence classes. It keeps the ultrapower so narrow that you can cleanly map it backward into the direct power.
That covers Theorem 4.31. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to Section 5.
Section 5, the climax, an application to real closed fields. We are building infinite continuous landscapes of numbers. The text brings up definition 5.8, the eta sub beta sets.
We have to talk about saturation here. Saturation is how gapeless a universe is. The real numbers are not fully saturated.
Right, because if you have a left set of 0.9 repeating and a right set of 1, there is no number strictly between them in standard reals.
Exactly. Felix Hausdorff defined an eta set as an ordered structure so dense that no matter what infinite left and right sets you pick, there is always a number strictly between them. It forces the universe to conjure infinitesimals and transfinite infinities to fill the gaps.
That covers definition 5.8. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to Theorem 5.1 and 5.13.
Theorems 5.1 and 5.13 introduce a staggering requirement. The index set must be built upon a strongly inaccessible cardinal. The cardinal is a left lambda, a left sub lambda.
A strongly inaccessible cardinal is a number so vast it serves as a boundary for the mathematical universe. You cannot reach it by taking power sets or massive unions of smaller infinities. It sits alone at an unreachable horizon.
So the author stacks the cumulative skyscraper all the way up to this unreachable horizon lambda. And they use a tails ultrafilter to quotient it.
Right. A tails ultrafilter gives 0 power to the initial timelines and absolute dictatorial power to the tail end of infinity. It biases the structure toward the horizon. And the theorem proves this exact combination results in an eta sub lambda set, a maximally saturated hyperreal field.
That covers theorems 5.12 and 5.13. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to corollary 5.32.
Corollary 5.32 is the ultimate conclusion. Under global choice, the cumulative power hierarchy over the class of all ordinals, when quotiented, is isomorphic to Conway's surreal numbers.
It is a transfinite architectural masterpiece. We started with basic functions looking back at their origins via theta. We applied democratic ultrafilters all the way to the class of all ordinals, and we mathematically synthesized the surreal numbers, the absolute largest possible ordered field.
That covers corollary 5.32. Have we missed any nuances?
I think we've thoroughly unpacked it. We've reached the end of the formal analysis.
This entire rigorous exercise has been incredible. But I want to connect this back to you, the listener. Think about the cumulative hierarchy. Standard math overwrites the past. It is non-cumulative. But in our skyscraper, the fundamental building blocks coexist alongside infinite layers of functions operating upon them, and equality is strict.
Nothing is ever truly overridden.
Right. So what if our own human cognition, or even the future of recursive AI, operates exactly like a cumulative power? We do not replace our foundational memories. We build layered functions of abstraction on top of them.
Oh, that is a profound analogy.
And true understanding only happens when we map those abstractions all the way down to their roots using a psychological theta function. We have to translate the high-level trauma or reaction down to the exact floor where it was born.
It reflects how complex systems actually sustain themselves without collapsing. The logic of origins matters.
Absolutely. Thank you for surviving this ultimate, unabridged deep dive with us. To map the boundary of truth and build a universe of numbers that contains everything, it is a tour de force. Keep exploring those foundations. We will see you next time.
All right, welcome everyone. Today, we are diving headfirst into a really cool paper. It's one of those that pulls back the curtain and shows you this hidden, beautiful unity in how mathematicians actually, well, how they build entire worlds. The idea is that there might be a single master blueprint for creating all these complex mathematical structures. So let's jump in and see how they did it. So right off the bat, we're hit with this huge question. And really, this is what model theory is all about. Think about it for a second. Let's say you've got something familiar, like the good old natural numbers, 1, 2, 3, and so on. How do you take that simple foundation and build something way, way bigger, something more powerful, but that, and this is the key, still has the same DNA as the original? How do you do that?
Okay, so for a very long time, mathematicians have had these two classic, super powerful tools in their toolkit to do exactly this. You can think of them as the standard gear, the tried and true methods for taking what you know and expanding your mathematical horizons.
Now, before we get any deeper, let's just make sure we're on the same page with this word structure. What do we even mean by that? Honestly, it's pretty simple. It's just a bunch of objects, could be numbers, could be points, whatever, and a set of rules for how they play together. Things like addition or multiplication or how they're ordered. The Lego analogy here is just perfect. You've got your bricks, and you've got the rules for how they're allowed to connect. That's it.
So these two methods we mentioned, they've been the absolute workhorses of this field for decades. I mean, for a long, long time, this is how it was done. They're both different ways of taking that initial structure, our set of Lego bricks, and using it to build something vastly more complicated and intricate. Okay, tool number one is called the direct power. And the core idea here is that you create a new set that's made up entirely of functions. So for instance, let's say you start with the real numbers. A new thing in your direct power structure would be a function, any function that spits out a real number for whatever you put into it. But here's the really important part. All the operations, like addition, are done point-wise. What does that mean? It just means if you want to add two of these functions together, you just add their outputs at every single point, one by one.
All right, now for tool number two, the ultra power. And you can really think of this as like a supercharged version of the direct power. It's built on the same idea, it uses functions, but it adds this incredibly powerful extra gadget called an ultrafilter. An ultrafilter, a good way to picture it is like a really, really picky sieve. It's a filter that goes through and decides exactly which properties from your original structure are going to be true in the new, bigger one. And it is incredibly precise.
So here's where it gets really interesting, because these two tools have very different strengths. Direct powers, they're great for sure, but they only preserve a specific class of logical statements, these things called horn sentences. You can just think of them as simple if-then rules. But ultra powers, whoa, thanks to that clever ultrafilter, they are way stronger. They preserve all first-order sentences, which are much more complex logical statements, and this means the new structure you build is elementarily equivalent to the original. It's basically a perfect logical mirror of the old one. It just happens to be way, way bigger.
So for years and years, that was the story. You had these two separate, distinct tools. You pick one or the other depending on what you need. But then this paper comes along and introduces a totally new idea, a more fundamental approach to building these worlds that, as we'll see, puts both of those old tools in a completely new light. And to understand this new idea, you first have to see the key limitation of the old ways. See, when you build a direct power or an ultrapower, the new things you create, all those functions, they kind of live in their own separate universe. The original numbers are over here and the new functions are over there. They don't mix. It's like they're on different floors of a building with no staircase. The paper calls this non-cumulative. And that right there brings us to the core, brilliant idea of this paper, the cumulative power. Instead of building a whole separate world, what if you just build in layers? At every single step, you take everything you already have and you add all the possible functions on that set to it. So you get the original numbers, and then the functions on those numbers, and then the functions on those functions, and so on. They all get to live and interact in the exact same, constantly growing universe. It's a totally different philosophy.
And you can see the process laid out right here. It's actually pretty elegant. You start with your base, let's call it A. Then, for the next level, you take everything in A plus all the functions you can make on A. Then for the next level, you take everything you just made plus all the functions you can make on that. You just keep repeating the process, layer upon layer. It's this beautiful self-building tower, where each new floor contains all the floors below it.
Okay, so we've got this new way of building things. It's neat, but you might be asking, so what? Why is this such a big deal? Well, this is where the big aha moment of the paper comes in. This isn't just another tool to add to the collection. It turns out this is the master tool. This right here, this is the punchline of the entire paper. It turns out those two classic powerful tools we talked about, direct powers and ultrapowers, they aren't really separate things at all. They're just different ways of looking at the same giant underlying structure, the cumulative power. You can get both of them from this one single source. So how on earth does that work? Let's walk through it. Everything starts with this incredibly rich, layered cumulative power. Remember, this is the one where everything from all the different levels coexists. This is our raw material. This is the master blueprint. Okay, now imagine you apply a specific rule to this massive structure. The rule is this. You decide that two things are the same if they behave identically at every single level, all the way down. The paper calls this hereditary identity. When you apply this rule, in math we call this taking a quotient, which is just a fancy way of saying you're grouping things together based on a rule, that huge complex cumulative power suddenly simplifies, and what you're left with is exactly a direct power. It just emerges. But what happens if we use a different rule? Let's take that ultra filter we mentioned before, that super picky sieve. If we use that as a rule for deciding what's the same, the cumulative power simplifies in a completely different way. And what pops out this time? An ultra power. It's incredible. The crucial point is that both of these classic constructions are really just shadows cast by this one, deeper, more fundamental object. Okay, look, that's a really elegant and beautiful idea, right? It tidies things up. But you've got to ask, does this actually matter? Is it just a neat trick, or does it let us do anything new? Well, the answer is a huge yes. And this gets to the very heart of why this whole thing is so exciting.
See, unifying these tools isn't just about making things look tidy on paper. It gives us a single, much more powerful, and much more systematic framework for actually constructing new and exotic mathematical objects. It's like finding out that two confusing, overgrown hiking trails are really just different ways to get to the same beautiful, wide-open highway. Suddenly, you have a much better way to get where you're going. And here's just a stunning example of its power. Using this single framework, you can actually construct hyperreal fields, number systems that have infinitesimals in them, at every single level of the hierarchy. But it gets even crazier. If you take the entire infinite structure, the whole shebang, you can build a field that is isomorphic to the surreal numbers. And if you know anything about the surreals, you know they are one of the most vast, mind-bogglingly huge number systems ever imagined. And this new method gives us a surprisingly clean path to building them, something that was way harder before.
So, when you boil it all down, the ultimate takeaway is this. This cumulative power thing acts like a single, unified foundation. It's like the primordial clay from which all these other, more familiar mathematical realities can be sculpted. All you have to do is choose the right lens to look through. And that, of course, leaves us with a pretty tantalizing question, doesn't it? This framework, it gives us a brand new way to build these strange and wonderful number systems we thought we already understood. But what else is out there? If this is the master blueprint, what other bizarre, beautiful, and completely new worlds are just waiting for us to construct them? Okay, what if I told you there's a single master blueprint that can be used to build entirely new mathematical universes? Well, today, we're going to dive into a paper that claims to have found exactly that.
You know, it's a question that sounds like it's pulled straight from science fiction, right? How do you build a completely new universe from an old one? But for mathematicians, this isn't fantasy. It's all about a deep, really creative process of construction, and we're about to see exactly how it works.
So, to really appreciate this new blueprint, we first have to take a trip back in time and visit the old kingdoms of mathematical construction. These were the powerful, time-tested tools that mathematicians were using for decades to expand their worlds.
First things first, what are we even building with? Well, the fundamental concept is something called a mathematical structure. And honestly, the best way to think of it is just like a Lego set. You have the bricks themselves, those are your objects, like numbers. And then you have the instruction manual, the rules for how they connect, like addition or multiplication. That's it. A set of objects and a set of rules. That's your structure.
For a long, long time, if you wanted to build a bigger, more complex world from a structure you already had, you basically had two main toolkits. And, importantly, everyone thought of these as completely separate, totally distinct methods. The first tool is called the direct power. So imagine you have your set of numbers. Now picture an almost endless collection of lists, where every single entry in the list is one of your numbers. To add two of these huge lists together, you just add the corresponding entries one by one. That's what pointwise means. It's simple, it's straightforward, and is a really powerful way to build a bigger world. Then there's the ultrapower. This isn't just a bigger structure, it's more like a perfect mirror image of the original. It uses this really sophisticated filter to make sure that every fundamental truth, every single basic property of the original world, is perfectly preserved in the new one. It's kind of like creating a high-fidelity copy that behaves exactly like the original, just on a much grander scale.
So for years, you had this trade-off. Direct powers were pretty easy to build, but they were a bit leaky. Some of the original structure's properties didn't quite make it through. Ultrapowers, on the other hand, were these flawless, perfect copies, but they were incredibly complex and difficult to construct. So that was the choice: simple and leaky, or perfect and complex.
But what if that whole choice was a false one? What if those two kingdoms were actually just part of the same continent all along? Well, that's the core idea behind this paper's big innovation, the cumulative blueprint.
And here's the key difference. Instead of building a new world next to the old one, this new method builds around it. The original elements, your starting numbers, are still right there, in the middle of all the action, and they can now interact with all the new, more complex things being created. It's not a copy, it's a genuine expansion.
So how does this expansion actually work? It's this incredible iterative process. You start with your original structure. Then you add a layer of all possible functions into it. But here's the genius move. For the next layer, you build functions on top of that new combined set. You just keep stacking layers, one on top of the other, building this sort of infinite mathematical skyscraper.
And what you end up with is this incredible unified ecosystem. Your original object, let's say the number 2, is now living in the same world and can interact directly with these vastly more complex, higher-level objects. Everything is connected in one single coherent reality.
Okay, so this is where it all comes together. We've built this new, vast structure. Now let's see how it reveals the master blueprint we've been talking about. Here it is, the big aha moment of the paper. Those old methods, the direct power and the ultra power, they aren't separate tools at all. They are just different ways of looking at this single, more fundamental thing called the cumulative power. The logic is actually beautifully simple. You start with just one object, this new cumulative power, and that's it. It's the master key, it's the source code. All the information you need to build those other structures is already contained right inside it.
So how do you give the old kingdoms back from this new empire? Well, it's like putting on different pairs of glasses. If you look at the cumulative power through one specific mathematical lens, it just snaps into focus and looks exactly like the direct power. Then you put on a different, more powerful lens, and boom, you see the ultra power. They were just different views of the same thing all along.
The analogy is just perfect. We thought we were looking at two separate kingdoms, but they were actually just different cities inside the same vast empire. We just needed the right map to see how they were all connected. Okay, so we've unified these big mathematical ideas. It's pretty cool. But why does this matter? What can we actually do with this new master blueprint?
So, what's the big takeaway here? Why go through all this trouble to unify these ideas? Well, it all boils down to one single, incredibly powerful advantage.
It gives mathematicians a unified theory of construction. Instead of having to choose between a leaky toolkit and a perfect but complex one, they now have a single foundational engine. And they can use it to not only build new worlds, but to understand the deep, hidden connections between them.
And this isn't just some abstract theory. No way. This blueprint can build some of the most exotic and powerful number systems ever imagined. Things like the hyper-real numbers, which is a system that includes truly infinite numbers and numbers that are infinitesimally small. I mean, smaller than any positive number you can even name. It can even build a surreal numbers, a totally mind-bending universe of numbers that contains all the others. This blueprint provides a single, elegant key to creating them all.
So here's the bottom line. Cumulative powers give us a single, unified foundation for constructing entirely new mathematical realities. It truly is a master key for creation.
And this leaves us with a pretty awe-inspiring final thought. If this one blueprint can build universes as wild as the hyperreals and the surreals, it really makes you wonder what other, even stranger mathematical worlds are out there just waiting to be constructed.
Welcome to The Explainer. Today, we're diving into a paper that uncovers this beautiful, hidden structure deep inside mathematics. It takes two tools that seem totally different and shows how they're actually, get this, just two sides of the same, much more powerful coin. Let's get into it. Okay, to get our heads around this, let's start with a really simple question. Imagine you've got one function, let's call it f, that just doubles any number you put in. And you've got another one, g, that just adds 1. So how would you combine them to make a totally new function? Well, the most obvious way, right? You just do it point by point. You take a number, you run it through both functions, and then you just add the two results together. Easy. But this super simple, almost intuitive method is actually the seed of a much, much bigger idea in mathematics. Yeah, this whole idea of building something new, point by point, is a really fundamental trick mathematicians use. It's kind of like using simple, familiar bricks to construct a whole new kind of building they've never seen before. This process actually has a formal name. It's called creating a direct power. Just think of it like this. You're taking a world you already get, like whole numbers and how to add them, and you're using that as a blueprint to build an entirely new world that's made of functions. And in this new function world, you can add the functions together, just like you did with the numbers. And think about the huge leap we just made here. We went from one simple calculation, like 2 plus 3, to an operation that combines two entire functions at every single point on the number line. It's like we're adding two whole landscapes together, matching up every peak and every valley. But, as we're about to see, this powerful upgrade, well, it's not quite perfect. So, we've built this new function world from the old number world. But is it a perfect copy? That's the million-dollar question, right? How much of the original rulebook does it actually follow? Is it a faithful recreation, or is it more like a blurry reflection? And the answer, which might surprise you, is no, it doesn't. You know, the basic stuff like a plus b equals b plus a, that carries over just fine. But some of the deeper, more subtle logical rules, they just break. A statement that was true in the original world might not be true anymore. And that limitation meant mathematicians needed a much more powerful tool. So they came up with something called an ultrapower. You can think of it like a magical photocopier. It doesn't just make a blurry copy. It creates a new structure that is a flawless, perfect clone of the original. In math, they say it's an elementary copy, which is a fancy way of saying that any logical statement that was true back in the original world is also true in the new one. It doesn't just follow some of the rules, it follows the entire logical rulebook perfectly. So for a long, long time, mathematicians had these two incredibly useful tools. You had the simple, easy-to-build direct power, and you had the logically perfect ultrapower. And everyone saw them as two completely separate ways of doing things. And this is where the paper we're looking at today makes its absolutely brilliant leap. The authors basically stepped back and asked this amazing question. They said, hold on, what if these aren't two different ideas at all? What if they're just two different ways of looking at a single, much bigger, more fundamental object that's hiding underneath them both? And what they found was exactly that. They uncovered this master structure, and they called it a cumulative power. And this is the huge revelation here. It's this more general, more expansive world that holds the potential for both of our other structures inside of it, just waiting to be shaped. Okay, so how do we get our old, familiar tools, the direct power and the ultra power, from this new master structure? Well, the key is this really cool analogy. I want you to think of the cumulative power as a giant raw block of marble. Seriously, just picture it. It's this massive, unformed block, and it contains everything you could possibly need. It's just full of potential. But to get something useful out of it, you have to start chiseling away the parts you don't want. So in math, this chisel has a specific name. It's called an equivalence relation. And that just sounds complicated, but it's really just a precise rule for deciding which things you're going to treat as being the same. For example, we all agree that the fractions 1/2 and 2/4 are equivalent, right? Even though they look different, they mean the same thing. That's an equivalence relation at work. And this is where it all comes together. It's amazing. You start with the same block of marble, the cumulative power. Now, if you pick up your first chisel, a rule that says two functions are the same only if they match up perfectly at every single point. Boom, you carve out the direct power. But what if you use a different chisel? What if you use this sophisticated mathematical sieve called an ultrafilter? This lets you create a new rule for sameness. It lets you say two functions are the same if they agree on a large set of points, even if they're different elsewhere. And when you use that rule, you carve out the perfect detailed ultrapower from the very same block of marble. Now, here's the crucial point. This is not just some abstract tidying up exercise for mathematicians. This new, unified way of looking at things provides a surprisingly direct path to one of the most bizarre and wonderful things in all of mathematics. It turns out that if you start with the simplest building blocks you can imagine, and you apply this cumulative power idea over and over, carefully choosing the right chisels at each stage, you can actually build one of the most incredible structures known to exist, the entire field of surreal numbers. And why on earth should you care about that? Because the surreals are absolutely mind-bending. They're a number system that doesn't just have one infinity, it has infinite levels of infinity. They have numbers that are infinitely small, infinitesimals, that are closer to zero than any fraction you can possibly write down. It is a number line so vast, so all-encompassing, it seems to contain every other number line inside of it. And really, that's what this paper shows us. Sometimes the biggest breakthroughs don't come from inventing something totally new, but from finding the hidden unity in the things we thought we already understood. It just leaves you wondering, right? What other master structures are out there, just waiting for us to find the right way to look at them?